Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight's gentle journey drifts towards something both familiar and impossibly strange. Light. Not just the soft glow of a bedside lamp or the pale shimmer of the moon through your window, but light as a limit. A boundary. A speed that nothing in the universe, at least nothing with mass, has ever been known to cross. Now, that idea alone is already a little curious. A speed limit built into reality itself. Not a suggestion, not a guideline, but a hard, unbreakable rule. And yet, it invites a question that feels almost inevitable. Like wondering what's at the edge of a map, or what lies just beyond the last visible star. What would really happen if you travelled at the speed of light? Not almost, not close, not 99.9% of it, but truly at light speed. What would you see? What would you feel? Would time pass the same way? Would the universe look familiar? Or would everything begin to shift into something unrecognisable? Before we ease into those answers, I'd love to know something simple. Where are you listening from tonight? And what time is it for you right now? It's a small question, but somehow fitting. A story about light, about time, about motion. And here we all are, scattered across the world, each of us in our own moment, our own quiet slice of the evening. If you find this journey soothing or interesting, or just a gentle way to let your thoughts slow down a little, I'd be ever so grateful if you gave the video a like and maybe subscribed. It helps this calm little corner reach others who might also be looking for a softer landing at the end of the day. Now get comfortable, let your shoulders relax just a little. There's no rush here, no need to understand everything all at once. We're simply going to wander through the idea together, step by step, like following a quiet path through something vast and unfamiliar. Because the speed of light is not just fast, it is, in a very real sense, the fastest anything can ever be. To get a feel for it, imagine flipping on a light switch in a dark room. The moment your finger presses down, the room fills with light instantly, or at least it feels that way. But even that isn't truly instant. Light is moving, travelling from the bulb to your eyes at an incredible pace. About 300,000 kilometres every second. That's fast enough to circle the Earth more than 7 times in a single second. Fast enough to travel from the Earth to the Moon in just over a second. Fast enough that, in everyday life, we treat it as if it's instantaneous, because compared to our human sense of time, it practically is. But here's where things start to become a little more interesting. Even though light is unimaginably fast, it still takes time to move. When you look at the Moon, you're not seeing it as it is right now. You're seeing it as it was about 1.3 seconds ago. When you look at the Sun, the light reaching your eyes left the Sun around 8 minutes earlier. And when you look at distant stars, you're often seeing light that has been travelling for years, decades, sometimes even millions of years. In a quiet way, every glance at the sky is also a glance into the past. And that alone tells us something important. Light doesn't just illuminate the universe, it carries information across it. It connects distant places, stitching together moments that would otherwise remain forever separate. Now imagine trying to keep up with that. Not just watching light travel, but moving alongside it, matching its speed, staying right there with it as it crosses space. At first, it sounds almost like a simple extension of something we already understand. After all, we can go faster and faster, can't we? Cars, planes, rockets. Each step brings us closer to higher speeds. So why not just keep going? Why not build something powerful enough, efficient enough, to push us all the way to light speed? That's where the universe quietly raises its hand and says, not so fast. Because as it turns out, speed doesn't behave the way we expect it to, especially when we start getting close to that ultimate limit. In everyday life, speeds add together in a simple, predictable way. If you're walking forward on a train, and the train is already moving, your speed relative to the ground is just your walking speed, plus the train's speed. It feels intuitive, almost obvious. But light doesn't follow that rule. No matter how fast you're moving, whether you're standing still, driving, or flying through space in a rocket, light always moves away from you at the same speed. Always. That's not just a curious detail. It's one of the most important discoveries in physics, and it leads directly into everything we're about to explore. Because if light's speed is always the same, no matter how fast you're going, then something else must adjust instead. And that something is time itself. But let's not rush ahead just yet. It's easy to get caught up in the more dramatic consequences, the strange distortions and mind-bending ideas. Instead, let's stay with the feeling of it for a moment. Imagine you're sitting inside a perfectly smooth, silent spacecraft. No vibrations, no noise, just a gentle sense of motion. Outside the window, the stars are scattered across the darkness, distant and steady. At first, you're moving slowly. Then gradually you begin to accelerate. There's no wind rushing past you, no sense of resistance. Space doesn't push back the way air does. So the only hint of your increasing speed is the way things outside begin to shift, ever so slightly. The stars ahead of you seem to draw closer together, as if they're being gently pulled toward a point in front of you. The ones behind you drift apart, stretching out into the darkness. You're not imagining it. Something is changing. And as your speed continues to climb, approaching that distant, unreachable limit, the universe itself begins to behave differently around you. Not because space is changing, but because your relationship to space and time is. That's the part that's easy to overlook. When we talk about speed, we tend to think of it as something simple, just moving from one place to another, faster or slower. But at extreme speeds, especially near the speed of light, speed stops being just about motion. It becomes something deeper, something that starts to reshape the way reality is experienced. Time doesn't tick the same way. Distances don't stay fixed. Even the order of events can begin to feel less certain. And yet, inside your spacecraft, everything feels normal. Your heartbeat continues at its usual pace. Your thoughts unfold just as they always have. If you glance at a clock, it ticks forward steadily, second by second, without hesitation. From your perspective, nothing unusual is happening at all. It's only when you compare your experience to someone else's, someone watching from far away, that the strangeness begins to reveal itself. And that difference, that quiet disagreement between observers, is at the heart of what makes light speed so fascinating. Because travelling at the speed of light isn't just about going fast. It's about stepping into a part of reality where the rules we rely on, the ones that feel so solid and dependable, begin to soften at the edges, where time stretches, where distances shrink, where the universe doesn't behave quite the way we expect it to. And as we continue, we'll take a closer look at what that really means. Not just in equations or theories, but in experience. What would it feel like to keep accelerating, getting closer and closer to that ultimate speed? What would happen to time, both for you and for everyone else? And why, no matter how powerful your spacecraft might be, there's a point you can approach but never quite reach. For now, just let the idea settle in gently. A universe with a built-in speed limit. A boundary that shapes everything from the way light travels to the way time itself unfolds. And somewhere within that, the quiet question that keeps pulling us forward. What would it really be like to go that fast? Picking up from that quiet question we left hanging in the air, it helps to slow things down for a moment and look more closely at what we mean when we say the speed of light. Because it's one of those phrases that sounds straightforward at first. Light travels very fast, faster than anything else. That part is easy enough to accept. But the deeper you look, the more it starts to feel less like a simple measurement and more like a fundamental feature of reality itself. So, what is it, really? At its most basic level, the speed of light is just that, a speed. About 299,000, 792 kilometers per second, a number so large that it almost stops feeling meaningful. It's difficult to picture something moving that quickly, because nothing in our everyday experience comes even remotely close. Even the fastest aircraft ever built would take hours to circle the Earth. Light does it in a fraction of a second. If you could somehow travel at that speed, you could go from one side of the planet to the other in less time than it takes to blink. But here's where things start to become a little more subtle. When physicists talk about the speed of light, they're not just talking about visible light, the kind that lets you see your surroundings. They're talking about something broader. Light is part of a larger family called electromagnetic radiation. That includes radio waves, microwaves, infrared, ultraviolet, X-rays and gamma rays. All of these travel at the same speed in a vacuum. So in a way, the speed of light is really the speed of all electromagnetic signals. It's the speed at which information, in its simplest form, moves through empty space. And that turns out to be incredibly important. Because it means that this speed isn't just about brightness or colour or vision. It's about how quickly anything can influence anything else across the universe. If something happens on a distant star, the earliest possible moment you could ever know about it is when the light or any signal travelling at that speed finally reaches you. Nothing can carry information faster than that. No message, no signal, no cause and effect. Light speed isn't just fast, it's the ultimate speed limit for the transfer of information itself. Now that might already feel like a big idea, but there's another layer to it, one that makes things even more interesting. You might expect that speed, like most things, depends on your perspective. If you're standing still and I'm moving quickly, we might measure speeds differently. That's how it works with cars, trains, planes. Motion is always relative. But light refuses to behave that way. No matter how fast you're moving, the speed of light remains exactly the same. Imagine you're in a spacecraft, moving at an enormous speed, perhaps faster than anything humanity has ever built. You shine a flashlight forward. Intuitively, you might expect that the light would move away from you at its usual speed, plus whatever speed your spacecraft already has. But that's not what happens. Instead, the light still moves away from you at exactly the same speed as it would if you were standing completely still. No extra boost, no stacking of velocities, just the same constant speed. This is one of the most surprising discoveries in all of physics, and it was confirmed through careful experiments long before anyone fully understood what it meant. At first, it caused a bit of confusion, because if speeds don't add together the way we expect, then something else must be adjusting behind the scenes to keep the speed of light constant, and that something else turns out to be space and time themselves. But before we step into that, it's worth pausing for a moment and considering just how unusual this is. In your everyday life, if you throw a ball forward while walking, the ball moves faster relative to the ground than it does relative to your hand. Speeds combine in a simple, intuitive way. Light ignores that rule entirely. It behaves as if the universe has decided very firmly that this particular speed must remain fixed no matter what. And that decision has consequences, because if the speed of light cannot change, then measurements of distance and time must adjust instead to keep everything consistent. That idea didn't fully come together until the early 20th century, when Albert Einstein looked at this strange behavior and realized that the only way it could make sense was if our assumptions about time were not quite right. Time, in his view, wasn't a universal ticking clock shared by everyone everywhere. It was flexible, dependent on motion, capable of stretching and compressing in ways that feel almost impossible at first glance. But again, we'll ease into that gently. For now, let's stay with the speed itself and what it represents. Because there's another quiet detail that often gets overlooked. When we say the speed of light, we usually mean its speed in a vacuum, in completely empty space. That's important, because when light travels through materials like air, water, or glass, it actually slows down. Not dramatically, but enough to measure. In water, for example, light moves at about 3/4 of its speed in a vacuum. In glass, it's even slower. That's why a straw in a glass of water looks bent. Light changes direction slightly as it slows down and then speeds back up again when it exits the material. So in everyday environments, light isn't always at its maximum speed. But in the emptiness of space, where there's nothing to interact with, it moves at its full, constant value. And that's the speed physicists are usually referring to, the true upper limit. And here's where things become quietly profound. That speed, often written as c, isn't just about light. It shows up everywhere in physics, in equations that describe energy, in relationships between space and time, in the structure of the universe itself. It's less like a property of light, and more like a built-in feature of reality that light happens to follow. In fact, one way to think about it is this. The speed of light is the speed at which cause and effect can propagate through the universe. It's the rate at which changes can ripple outward. The maximum speed at which anything meaningful, any interaction, any influence can travel. And because of that, it quietly shapes everything. It determines how quickly stars can communicate their presence across space. It limits how fast particles can move. It even affects how we define distance and time in the first place. In modern physics, distance and time are deeply connected, almost like two sides of the same coin. And the speed of light acts as the conversion factor between them. It's what ties space and time together into something unified. But that connection comes with a price. If you try to move faster and faster, getting closer to that speed, the universe doesn't let you simply add more velocity the way you might expect. Instead, it begins to resist in a very particular way. Not with friction, not with air resistance, but with something more subtle. Energy. The closer you get to the speed of light, the more energy it takes to accelerate further. At first, the increase is manageable, then it grows more demanding, and as you approach that ultimate limit, the required energy rises more and more steeply, until, in theory, it becomes infinite. And that's the key point. Reaching the speed of light isn't just difficult, it's fundamentally impossible for anything with mass, because it would require an infinite amount of energy to get there. But again, we'll explore that more carefully as we go. For now, it's enough to notice the pattern. Light speed isn't just a number, it's a boundary, a limit that sits quietly at the edge of what's physically possible. And unlike most limits we encounter, it doesn't feel like a barrier you could eventually overcome with better technology or more powerful engines. It feels more like a rule woven into the fabric of the universe itself, something that doesn't bend, something that doesn't yield, and yet it's also something we can approach, closer and closer step by step, as our speeds increase and our understanding deepens. And as we do, the universe begins to behave in ways that are both fascinating and, at times, a little counterintuitive. Because the closer you get to that limit, the more the familiar rules start to shift. Time doesn't pass the same way. Distances don't remain fixed. Even the sequence of events can begin to depend on who is observing them. All of that unfolds from this one simple idea, that the speed of light is constant, always the same, no matter what, and that quietly changes everything. Somewhere along the way, as the idea of light speed settles into place, a quiet realization begins to form. If this speed really is the ultimate limit, then the natural next question almost asks itself, why? Not just why is it difficult to reach, but why is it impossible? What is it about the universe that draws such a firm line and says, this far and no further? At first glance, it might seem like a problem of engineering. Perhaps we just don't have powerful enough engines yet. Maybe with better technology, stronger materials, or more efficient fuels, we could keep accelerating until we finally catch up to light. That's a very human way of thinking about limits. Most boundaries we encounter can eventually be pushed, refined, or overcome with enough effort. But this one is different. The reason nothing with mass can reach the speed of light isn't about technology. It's not about materials or fuel or clever design. It's about the way energy, motion and mass are tied together at a fundamental level. And to understand that, it helps to imagine the process of speeding up in a slightly different way than we're used to. Think back to something simple, like pushing a heavy object across the floor. At first it resists a little, but once it starts moving, it becomes easier to keep it going. If you push harder, it moves faster. There's a clear, direct relationship between how much effort you apply and how quickly the object speeds up. That intuition works well at everyday speeds, but as you begin to approach the speed of light, that relationship starts to change in a very particular way. Instead of each push giving you a similar increase in speed, each push begins to have a smaller and smaller effect. You can keep adding more energy, keep applying more effort, but the increase in speed becomes less noticeable. It's as if the universe is gently resisting your attempt to go faster, not by stopping you outright, but by making each step forward a little more difficult than the last. And that resistance grows. At first it's subtle, then it becomes more pronounced, and as your speed continues to climb, getting closer and closer to light speed, something remarkable happens. The energy required to increase your speed begins to rise dramatically, not linearly, not steadily, but steeply. In fact, the closer you get to the speed of light, the more that required energy begins to climb toward infinity, which leads to a rather unavoidable conclusion. To actually reach the speed of light, you would need an infinite amount of energy. Not just a lot, not an enormous amount, literally infinite. And that's the point where the universe quietly closes the door, because no matter how advanced your spacecraft might be, no matter how efficient your engines, you cannot supply infinite energy. It's not just impractical, it's impossible. But why does this happen? Why does energy behave this way at high speeds? To answer that, we need to look at something that feels familiar, but changes its meaning a little when we move into this realm. Mass. In everyday life, mass is simple. It's a measure of how much stuff something contains. A heavier object has more mass, and it takes more effort to move or accelerate. That's straightforward enough. But as an object moves faster and faster, especially at speeds approaching light, its relationship with mass begins to shift. It's not that the object suddenly gains more material or becomes physically larger. Instead, its resistance to acceleration increases. From the outside, it behaves as if it's becoming more massive. So each time you try to push it faster, you're effectively pushing something heavier than it was before, and that heaviness continues to grow as the speed increases. The closer you get to light speed, the more extreme this effect becomes. Your spacecraft, your body, every particle inside you begins to resist acceleration more and more strongly. It's not something you would feel directly inside the ship. From your perspective, everything still seems normal. But to an outside observer, your motion is becoming increasingly difficult to change. And that's where energy comes back into the picture. When you apply energy to something, you expect it to translate into motion, faster movement, higher speed. But at these extreme velocities, more and more of that energy goes into increasing this effective resistance instead. It's like trying to push a door that becomes heavier every time you lean into it. At first it moves easily, then it becomes harder, then harder still, until eventually, no matter how much force you apply, it simply won't budge any further. That's what happens as you approach the speed of light. You can get closer, always closer, but never quite there. Now, there's another way to think about this that adds a different kind of perspective. Earlier, we touched on the idea that the speed of light is not just about motion, but about the structure of space and time themselves. In Einstein's view, space and time are woven together into a single fabric, and the speed of light acts as a kind of conversion factor between them. So when you move through space, you're also, in a sense, moving through time. At everyday speeds, almost all of your motion is directed through time. You move forward through it at a steady rate, 1 second per second, without noticing anything unusual. But as your speed through space increases, something subtle begins to shift. More of your motion is directed into space, and less into time. This is why time begins to slow down for objects moving at high speeds. It's not that time itself is stopping, it's that your movement through it is being redistributed. And as you approach the speed of a light, this effect becomes more and more extreme. Your motion through time slows further and further, until, at the limit, something remarkable happens. From the perspective of an external observer, your movement through time would effectively come to a halt. That doesn't mean you would freeze or become aware of anything unusual inside your own frame of reference. Your internal experience would still feel normal. But relative to the rest of the universe, your clock would appear to stop. And this connects directly back to the energy problem. Because reaching the speed of light would mean completely halting your progression through time relative to the outside world. And the universe doesn't allow that for anything with mass. It's not just a technical limitation, it's a structural one. Objects with mass are bound to experience time in a certain way. They can slow their passage through it, but they can't stop it entirely. Only things without mass, like light itself, can exist at that boundary. Photons don't experience time in the way we do. From their perspective, if such perspective can even be meaningfully described, the journey from emission to absorption is instantaneous. But for anything with mass, even something incredibly small, that limit remains out of reach. There's also a quieter implication hidden within all of this. The speed of light isn't just a limit on how fast you can go, it's a limit on how quickly cause and effect can propagate. If you could travel faster than light, you could, in theory, outrun cause and effect itself. Events could begin to happen out of order, effects might precede their causes. The structure of reality would start to unravel in ways that are difficult to even describe clearly. So in a sense, this limit isn't just a restriction, it's a kind of protection, a way of preserving the order of events, the consistency of cause and effect, the basic logic that allows the universe to make sense at all. And that's perhaps the most interesting part. What first appears to be a frustrating boundary, something that prevents us from going faster, turns out to be deeply connected to the stability of reality itself. Without it, the universe would behave very differently. Now, all of this might sound a little abstract, but it leads directly into something we can begin to feel more intuitively. If reaching the speed of light is impossible, what happens as you get close? What does it actually feel like to approach that limit? Not in equations or numbers, but in experience. What would happen to time as you continue accelerating? How would the outside world appear to change? And what would it be like inside that spacecraft as the universe slowly begins to behave in ways that don't quite match your everyday expectations? At some point, as the idea of approaching light speed settles in, attention naturally shifts towards something more personal than distance or energy. Not how far you could travel or how fast you might go, but something quieter and much closer to home. Time. Because if reaching light speed changes the structure of reality, then it must also change the way time flows. And as it turns out, this is where things begin to feel less like physics and more like something almost intimate. Not dramatic, not chaotic, just different. Imagine once again that same spacecraft, steady and silent, drifting through space. You're inside, comfortably seated, watching the distant stars through a wide, clear window. The engines have been running for a while now, gently but continuously accelerating you forward. Nothing feels unusual at first. Your breathing is steady. Your thoughts move at their usual pace. If you glance at a clock on the wall, it ticks forward with perfect regularity. 1 second, then another, just as it always has. From your perspective, time is behaving exactly as expected. And that's the first important thing to notice. No matter how fast you go, no matter how close you get to the speed of light, your own experience of time will always feel completely normal. Your internal clock, your heartbeat, your thoughts, they all remain in sync with one another. There's no sudden slowing, no strange pauses, no sense that anything is off. But the story changes when someone else looks at you from the outside. Imagine a second observer, far away, watching your spacecraft as it continues to accelerate. From their point of view, something subtle begins to happen. At first, it's barely noticeable. Your movements appear just slightly slower than expected. A small delay here, a faint stretching of time there. But as your speed increases, that effect becomes more pronounced. Your clock, the one that looks perfectly normal to you, begins to tick more slowly from their perspective. Not metaphorically, not as an illusion, actually slower. This phenomenon is called time dilation, and it's one of the most well-tested and well-understood consequences of moving at high speeds. The faster you go, the slower your time passes relative to someone who is not moving with you. And this isn't just a theoretical idea. It has been measured many times in carefully controlled experiments. Atomic clocks, some of the most precise timekeeping devices ever created, have been placed on airplanes, flown around the world, and then compared to identical clocks that remained on the ground. When the clocks were brought back together, they didn't agree. The ones that had been moving, even at the relatively modest speeds of commercial aircraft, had experienced slightly less time. Not enough to notice without extremely precise instruments, but enough to confirm that the effect is real. Time, it seems, is not universal. It doesn't flow at the same rate for everyone. Instead, it depends on how you move. Now, it's worth pausing here, because this idea can feel a little slippery at first. How can time itself change? After all, we're used to thinking of time as something steady, a kind of invisible river flowing at the same pace for everyone, everywhere. But that assumption, as it turns out, doesn't quite hold up. Instead, time behaves more like a personal measurement, tied to your own path through the universe. Two people moving differently can experience time differently, and neither of them is wrong. Each is simply following their own clock. Returning to the spacecraft, let's continue that journey. As your speed increases further, getting closer and closer to the speed of a light, the difference between your experience and the outside observers becomes more dramatic. From their point of view, your clock slows more and more, your movements stretch out, your actions take longer. Eventually, if you could somehow get extremely close to light speed, the effect would become profound. For every second that passes for you inside the spacecraft, much more time would pass for the outside observer. Minutes, hours, even years, depending on how close you get to that limit. But inside the ship, nothing feels unusual. That's the part that often surprises people the most. You wouldn't feel slowed down. You wouldn't notice anything strange about your own experience of time, because everything around you, your body, your thoughts, your instruments, is slowing down together in perfect synchrony. It's only when you compare your clock to someone else's that the difference becomes clear. And this leads to one of the most fascinating consequences of time dilation. If you were to travel at a speed very close to light speed for an extended period, and then return, you would find that much more time had passed for everyone else. You might have aged only a few years, but on Earth, decades could have gone by. This idea is often illustrated with something known as the twin scenario. One twin stays on Earth, living their life at a normal pace. The other boards a spacecraft, travels at near light speed, and eventually returns. When they reunite, the travelling twin is younger, not because of any biological trick, not because of suspended animation, but because their time literally passed more slowly. It's not a matter of perception, it's a difference in the actual amount of time experienced, and that's what makes it so remarkable. Time dilation isn't just about how things look, it's about how things are. Now, you might wonder why this happens. Why should motion affect time at all? The answer lies in the deeper structure of space and time, and the role that the speed of light plays within it. Earlier, we touched on the idea that the speed of light is constant for all observers. No matter how fast you're moving, light always travels at the same speed relative to you. That simple rule turns out to have far-reaching consequences. Because if the speed of light must remain constant, then something else has to adjust to make that possible, and that something is time. One way to picture it gently is to imagine that there's a kind of trade-off taking place. As you move faster through space, your movement through time changes. It's not the time itself is being slowed down in a global sense. It's that your path through space-time, the combined fabric of space and time, is shifting. At everyday speeds, almost all of your motion is directed through time. You move forward steadily, second by second, without noticing anything unusual. But as your speed through space increases, more of your motion is directed into space and less into time. The faster you go, the more pronounced this effect becomes, until, near the speed of light, your motion through time becomes very small compared to your motion through space, and that's what we perceive as time dilation. Now, there's another subtle aspect to this that's worth considering. From your perspective inside the spacecraft, it might seem as though the outside world is the one behaving strangely. If you could observe Earth as you travel at near light speed, you would see its clocks running faster, events unfolding more quickly. Time, for them, would appear to be accelerated. This symmetry is important. Each observer sees the other as experiencing time differently. There's no absolute reference point that says one is correct and the other is wrong. Instead, both perspectives are valid within their own frames of reference. It's only when you come back together and compare clocks directly that the difference becomes clear. And when you do, the travelling observer will have experienced less time. That's the measurable outcome. Now, beyond the science, there's something quietly thought-provoking about this idea. The notion that time is not fixed, that it can stretch and compress depending on how you move, that two people can live through different amounts of time simply because they follow different paths through space. It adds a certain depth to something we usually take for granted. Because in everyday life, time feels steady, reliable, predictable, but at high speeds, it reveals a flexibility that's almost hidden from us. A reminder that the universe is more intricate than it first appears, and that even something as familiar as time can behave in unexpected ways. A clock sits quietly on the wall of your spacecraft, ticking in perfect rhythm, each second following the last without hesitation. Nothing about it seems unusual. The sound is steady. The motion is familiar. If you didn't know any better, you might assume that time inside the ship is behaving exactly as it always has. And from your perspective, it is. That's the gentle trick at the heart of time dilation. It doesn't feel like anything. It doesn't announce itself. There's no moment where you suddenly notice time slowing down around you. Instead, it unfolds quietly, only becoming visible when you compare your experience to someone else's. Because while your clock ticks normally for you, to someone watching from far away, it does something very different. It slows. Not metaphorically, not as an illusion, actually slows. To ease into this, it helps to step away from spacecraft for a moment and think about something simpler. Imagine a kind of clock that doesn't rely on gears or springs but on light itself. Picture two mirrors facing each other, one above the other, with a beam of light bouncing back and forth between them. Each time the light hits a mirror and reflects, you count one tick. Up and down, back and forth, the rhythm is steady and predictable. This is sometimes called a light clock, and while it's a simplified idea, it captures something essential about how time can be measured. Now imagine that this light clock is inside your spacecraft. When the ship is at rest, the light simply travels straight up and down between the mirrors. The distance is short, the path is direct, and the ticks occur at a regular pace. But once the spacecraft begins to move, something interesting happens. From the perspective of someone outside the ship, the light is no longer moving straight up and down. Because the ship itself is moving forward, the light has to travel along a diagonal path, tracing a kind of zigzag as it bounces between the mirrors. It's still moving at the same speed because the speed of light never changes, but now it has a longer path to travel, and if the path is longer, while the speed remains the same, then each tick takes more time. So to the outside observer, the clock appears to tick more slowly. Inside the ship, however, nothing has changed. The light still moves straight up and down relative to you. The mirrors are at rest in your frame of reference, and the clock behaves exactly as expected. Both perspectives are correct, and that's the key. Time dilation isn't about something going wrong with the clock. It's about the fact that time itself is not the same for different observers moving relative to one another. The faster the spacecraft moves, the more pronounced this effect becomes. At everyday speeds, it's so small that it's impossible to notice without extremely precise instruments. But as you approach the speed of light, the difference grows larger and larger. To get a sense of it, imagine your spacecraft accelerating to a significant fraction of light speed, perhaps 80 or 90%. Inside, your clock continues ticking normally. But from Earth, someone watching you would see those ticks stretched out. What feels like 1 second to you might correspond to several seconds for them. Push the speed even closer to light, and the effect becomes dramatic. At 99% of light speed, your time slows so much relative to Earth that for every second you experience, many seconds pass for those who remain behind. At 99.9%, the difference grows even more extreme. And as you continue approaching that ultimate limit, the gap widens further still. This isn't a gradual, gentle scaling. It accelerates. The closer you get to light speed, the more rapidly time dilation increases, which means that even small increases in speed near that limit lead to large changes in how time is experienced relative to others. Now, it's worth returning to something we touched on earlier, because it becomes especially important here. From your perspective, nothing feels different. Your thoughts, your reactions, your perception of time all remain perfectly normal. If you were to read a book, the words would flow at the same pace they always have. If you were to speak, your voice would sound unchanged to you. Time, for you, is steady. It's only when you compare your clock to someone else's that the difference becomes apparent, and that comparison reveals something quite profound. Time is not absolute. It doesn't flow at the same rate for everyone, everywhere. Instead, it depends on how you move. This can feel a little unsettling at first, because it challenges one of our most basic assumptions. We tend to think of time as universal, a shared background against which everything happens. But time dilation shows us that this isn't quite the case. Each observer carries their own time with them, shaped by their motion through space. And those different times can diverge in measurable, meaningful ways. Now there's another layer to this that adds a kind of quiet elegance to the idea. Earlier we spoke about motion through space and motion through time as being connected. As you move faster through space, your motion through time changes. One way to picture this is to imagine that your total motion through space-time is always the same, but how it's divided between space and time can vary. At rest, almost all of your motion is through time. You move forward steadily, second by second. As you begin to move through space, some of that motion shifts. More of it is directed into space and less into time, so your progression through time slows down relative to someone who is not moving with you. This isn't something you would feel directly, but it's something that becomes very clear when you compare clocks, and that brings us back to the spacecraft. Imagine that you embark on a long journey, travelling at a speed very close to that of light. From your perspective, the trip might take only a few years. You age normally. Your body follows its usual rhythms. Everything feels consistent. But when you return to Earth, you find that much more time has passed there. Friends have grown older. Landscapes have changed. Entire decades may have slipped by, not because you were asleep or frozen or unaware, but because your time moved differently. And this leads to one of the most fascinating consequences of time dilation. It allows, in a very real sense, for travel into the future, not by jumping forward suddenly, but by moving along a path where less time passes for you than for others. It's not science fiction. It's a direct result of the way time behaves at high speeds. Of course, reaching those speeds is an enormous challenge, as we've already begun to see. But the principle itself is well established, and it has been confirmed through countless experiments. Even the satellites that orbit Earth experience a small amount of time dilation due to their speed. Their clocks tick slightly differently than those on the ground. Engineers have to account for this when designing systems like GPS, because even tiny discrepancies can lead to significant errors over time. So this isn't just an abstract idea, it's something that has practical consequences in the real world. Now there's one more subtle point worth considering. When we talk about time slowing down, it's easy to imagine that there's some kind of universal clock that is being altered. But that's not quite right. Each observer has their own clock, and each clock is valid within its own frame of reference. There's no single, absolute time that everyone agrees on. Instead, time becomes something more personal, more dependent on your path through the universe. And that shift from a universal time to a collection of individual times is one of the most important insights of modern physics. It changes the way we think about events, about simultaneity, about the relationship between past, present, and future. But for now, it's enough to stay with the feeling of it. A clock that ticks steadily in your own experience. A second that always feels like a second. And yet, when viewed from another perspective, that same second stretches, becomes longer, slows down, quietly, consistently, without any sense of strain or disruption. A quiet hum fills the cabin, steady and almost reassuring, as if the spacecraft itself is gently reminding you that everything is working exactly as it should. There are no sudden jolts, no dramatic vibrations, no sense of rushing wind, just a smooth, continuous motion, so even that begins to fade into the background. If you didn't look outside, you might not even realize how fast you're going. That's one of the first things that tends to surprise people when they imagine traveling at extreme speeds. Motion, on its own, doesn't feel like anything. It's acceleration that you notice, the push back into your seat, the subtle shift in balance, the feeling that something is changing. But once that acceleration becomes steady, or if it stops entirely, the sensation disappears. So inside this spacecraft, as it continues its journey closer and closer to the speed of light, your experience remains calm, predictable, almost ordinary. You float or sit or move around depending on how the ship is designed. Your hands behave the way you expect them to. Objects fall or drift just as they would under the conditions inside the cabin. Your body follows familiar rhythms. You breathe in and breathe out. Your heart continues its quiet, steady work. Your thoughts unfold at the same pace they always have. There's no internal signal telling you that something extraordinary is happening. And that's the gentle contradiction at the center of this whole idea, because from the outside, everything about your journey is becoming more and more unusual. But from the inside, it feels almost completely normal. If you were to check a clock, it would tick forward in perfect rhythm. 1 second, then another, without hesitation. If you were to prepare a meal, it would cook in the usual amount of time. If you were to sleep, your rest would feel as long or as short as it always does. Nothing inside the ship behaves strangely. Everything slows together, including you. That's why the experience remains so consistent. It's not that you're immune to the effects of travelling at high speed. It's that those effects apply to everything within your frame of reference at once. Your body, your environment, your instruments, they all remain synchronized. So there's no contrast for you to notice, no mismatch to draw your attention. Now, consider something simple, like a conversation. If you were speaking with someone else inside the spacecraft, your words would flow naturally. The timing of speech, the pauses, the rhythm of interaction, everything would feel just as it does in any other setting. You wouldn't hear your voice slow down. You wouldn't perceive their responses as delayed. Because within the shared environment of the ship, time is behaving consistently for both of you. It's only when you compare your experience to someone outside that the difference becomes apparent. But inside, there's no such comparison. Only the present moment unfolding in a steady, familiar way. Now, let your attention drift toward the window. Because while your internal experience remains calm and unchanged, the view outside begins to tell a different story. At lower speeds, space appears as it always does. Stars scattered across the darkness, distant and unmoving, their light steady and soft. But as your speed increases, approaching a significant fraction of the speed of light, subtle changes begin to appear. At first, they're easy to overlook. The stars ahead of you seem slightly brighter. The ones behind you seem dimmer. It's not dramatic, just a faint shift, like adjusting the brightness on a screen by a small amount. But as you continue to accelerate, that effect becomes more noticeable. The stars in front of you begin to cluster toward a central point, as if they're being gently drawn inward. Their light grows more intense, more concentrated. Meanwhile, the stars behind you spread out, fading into a softer, more distant glow. This is a result of how light behaves when you move at high speeds, something we'll explore more fully a little later. But from your perspective, it's simply what you see. The universe ahead compresses, the universe behind stretches, and yet, even this doesn't feel overwhelming. It's gradual, quiet, almost like watching a slow transformation rather than a sudden shift. Now, there's another detail that often surprises people. Even though you're travelling at an enormous speed relative to the outside world, you don't feel like you're moving fast. There's no sense of rushing past things, no wind, no blur of motion like you might experience in a car or a train. Because in space, there's no medium to move through in the same way. And because everything you observe is affected by your motion, the usual cues we rely on to judge speed begin to fade. Speed, in this context, becomes relative. Without a clear reference point, without something nearby to compare against, it's difficult to feel how fast you're going. So instead of feeling like you're racing through the universe, it might feel more like the universe is slowly rearranging itself around you. Now think about something even simpler. Time as you experience it. We've already touched on how time dilation affects your journey relative to others, but inside the ship, your perception of time remains steady. If you set a timer for 1 hour, that hour will feel like 1 hour. If you spend a day travelling, it will feel like a day. There's no sense that time is slipping away more slowly or more quickly. It just flows, quietly, consistently, as it always has. And that consistency is what makes the experience so gentle, because even though you are participating in one of the most extreme conditions the universe allows, your direct experience remains grounded, familiar, understandable. Now imagine spending weeks, months, or even years aboard this spacecraft. Your routines would form just as they do anywhere else. You would wake, eat, rest, think, perhaps work or explore or simply observe. The passage of time would feel natural. You would age as expected. Your body would follow its usual patterns. Nothing about your internal experience would hint at the extraordinary nature of your motion. And yet, outside, something very different would be unfolding. Time for others would be passing more quickly. Events would be moving forward at a different pace. But from inside the ship, that reality remains distant, unfelt. Now, there is one important detail to consider. While your internal experience remains normal, the process of accelerating to these speeds is not entirely without sensation. If the spacecraft is continuously accelerating, you would feel a steady force, much like gravity, pressing you gently in the opposite direction of motion. This could be used intentionally, creating a comfortable environment where you can walk and move as if under Earth-like gravity. But once the acceleration stabilizes or stops, that sensation fades, and what remains is the quiet, almost serene experience of motion without resistance. Now consider how your sense of distance might begin to shift. At these speeds, something subtle happens to the way distances behave relative to your motion. The space ahead of you begins to compress. Distances along your direction of travel appear shorter. This means that, from your perspective, destinations may seem closer than they would to someone at rest. But again, this isn't something that feels dramatic or disorienting. It's more like a quiet adjustment in how far things appear, a gentle shortening of the path ahead. And when combined with the way time behaves, it creates an interesting effect. From your perspective, long journeys may take less time than expected. Not because you're moving faster in your own frame of reference, but because the distance itself has changed. It's a subtle interplay between space and time, one that becomes more noticeable as your speed increases, but inside the ship it simply feels like the journey unfolding naturally. Now, there's a final thought to rest with for a moment. Despite everything we've described, the extraordinary speeds, the shifting appearance of the universe, the differences in time, your experience remains grounded in something very simple. The present moment. Each second as it passes feels complete, whole, unchanged. You don't experience the universe as something distorted or broken. You experience it as something continuous, flowing, and that's perhaps the most surprising part. Travelling near the speed of light doesn't feel like stepping into chaos. It feels like carrying your normal experience into a place where the rules behind the scenes have quietly shifted, where the deeper structure of reality is different, but your perception remains steady. Far beyond the quiet interior of your spacecraft, where everything feels steady and familiar, the rest of the universe is keeping its own pace, not matching yours, not waiting, simply continuing forward, second by second, in a way that slowly begins to separate your experience from everything else. And that separation at first is almost impossible to notice. If someone on Earth were watching you through a powerful telescope as your journey begins, they wouldn't see anything particularly unusual. Your spacecraft would move away, gradually picking up speed, your signals still arriving, your onboard clock still ticking in a way that seems mostly consistent. But as your velocity increases, something subtle begins to shift. From their perspective, your time starts to stretch. Your movements, your actions, even the blinking of lights inside your ship, all begin to slow down. Not dramatically at first, just enough to feel slightly out of sync, like a video playing at a slightly reduced speed. They might not even notice it right away. But given enough time, the difference becomes undeniable. Your clock, the one that feels perfectly normal to you, begins to fall behind theirs. And as your speed continues to climb, that gap widens. Minutes for you might correspond to many more minutes for them. Hours for you could stretch into days. And if you were travelling extremely close to the speed of light, something even more striking would happen. From their point of view, your time would appear to almost stand still. Your spacecraft would seem frozen, or nearly so, creeping forward at an almost imperceptible pace, while everything else around them continues as usual. But that's only one side of the story. Because from inside your spacecraft, the situation appears reversed. You don't feel slowed down, you don't experience any delay in your own time. Instead, it's the outside world that begins to change. If you had a way to observe Earth clearly during your journey, you would notice something unusual. Clocks on Earth would appear to tick faster, not wildly, not instantly, but steadily accelerating compared to your own. At first, it might seem like a small discrepancy, a slight mismatch in timing, but as your speed increases, the effect becomes more pronounced. Events on Earth would begin to unfold more quickly, days passing in what feels like hours, hours slipping by in what feels like minutes. And as you approach even closer to the speed of light, that acceleration becomes dramatic. Entire years could pass on Earth while you experience only a short period of time. Cities would change, seasons would cycle rapidly, generations might come and go, all while your own experience continues at its usual pace. And yet, from your perspective, nothing about your own time feels unusual. That's the quiet symmetry of it. Each observer sees the other as experiencing time differently. To them, you are slowed. To you, they are accelerated. Both perspectives are valid. Both are correct within their own frame of reference. But when the journey ends, when you return and compare clocks directly, the difference becomes clear. Less time will have passed for you. More time will have passed for them. And that difference isn't just theoretical. It's real, measurable, a direct consequence of how time behaves at high speeds. Now, it's worth pausing for a moment to consider what this would feel like on a more personal level. Imagine leaving Earth on such a journey. You say goodbye to friends, to family, to familiar places. From your perspective, the trip lasts a manageable amount of time, months, perhaps years. You live through those moments normally. You think, you rest, you observe. Nothing about your internal experience suggests that anything unusual is happening. But when you return, everything has changed. People you knew may have grown older, or perhaps are no longer there. Places may look different. Technology, culture, even language might have shifted. Not because you travelled far, but because you travelled fast. And time, for everyone else, continued to move forward at its own pace. That's the part that often feels the most striking. Not the speed itself, but the separation it creates. A quiet drifting apart in time. You remain anchored in your own experience while the rest of the world moves ahead. Now, there's another subtle detail hidden within all of this. When we say that time on Earth appears to speed up from your perspective, it's not just clocks that are affected. Everything speeds up. Conversations, movements, changes, all of it unfolds more quickly. If you were watching a live broadcast from Earth, it would begin to feel like watching something on fast forward. People moving more quickly, voices slightly higher in pitch, events compressed into shorter spans of your time. But again, this isn't something you would feel directly as a distortion. It would simply appear as the natural consequence of your relative motion. Now consider the flow of cause and effect. From your perspective, events on Earth still happen in order. One thing leads to another. Nothing appears out of sequence. But the timing between those events shrinks. The intervals shorten. So while the structure of events remains intact, their pacing changes. It's as if the world outside is moving along a faster timeline than your own. And that difference continues to grow as your speed increases. Now there's something quietly profound about this. The idea that time is not shared equally, that two observers can move through it at different rates, each experiencing their own version of its passage. It challenges the way we usually think about time. We tend to imagine it as something universal, a single, steady flow that carries everything forward together. But here, that assumption begins to soften. Time becomes something more personal, something tied to your motion, your path, your journey. And that leads to an interesting realization. When you travel at high speeds, you're not just moving through space, you're moving differently through time. Your experience of the universe becomes unique, not just in where you are, but in when you are, and that difference grows the closer you get to the speed of a light. Now, there's one more aspect to consider: communication. If you were sending signals back to Earth during your journey, those signals would also be affected by your motion. From Earth's perspective, your messages would arrive more slowly, stretched out over longer intervals, but from your perspective, their replies would arrive more quickly. Compressed into shorter spans of your time, this creates a kind of asymmetry in communication, a mismatch in how time is experienced on each side. But again, each perspective remains consistent within its own frame of reference. Now, all of this might sound a little distant, a little abstract, but it leads directly into something we can explore more concretely. Because as your speed continues to increase, it's not just time that changes, space itself begins to behave differently. If time behaves differently at high speeds, it's natural to wonder whether distance remains unchanged, whether space itself holds steady, or whether it too begins to shift in quiet, unexpected ways. And as it turns out, it does. But much like time dilation, it doesn't announce itself in any dramatic fashion. It doesn't feel like the universe suddenly folding in on itself or collapsing into something strange. Instead, it reveals itself gently, through perspective. To ease into it, imagine once again that spacecraft moving steadily forward, faster and faster, approaching the speed of light. Inside, everything still feels calm. Your surroundings remain familiar. The walls of the ship haven't changed. The distance from one end of the cabin to the other feels exactly the same. If you were to measure it, you would get the same result every time. Nothing inside your frame of reference appears compressed or distorted. But now consider what happens when you look outward, toward the direction you're travelling. There's a distant star ahead, one you've chosen as your destination. From Earth's perspective, that star is many light years away, a vast distance, one that would normally take an enormous amount of time to cross, even at very high speeds. But from your perspective, something subtle begins to happen. As your speed increases, the distance to that star begins to shrink. Not because the star is moving closer in the usual sense, not because space is being pulled or rearranged in a visible way, but because the structure of space itself, along your direction of motion, is changing relative to you. This effect is known as length contraction, and like time dilation, it depends entirely on motion. From the perspective of someone at rest, the distance between 2 points remains unchanged, but from the perspective of someone moving at a high speed, distances along the direction of motion appear shorter. So as your spacecraft accelerates, the space between you and your destination compresses. At moderate speeds, this effect is extremely small, so small that it's practically impossible to notice in everyday life. But as you approach the speed of light, it becomes more significant, and then more noticeable, and eventually quite dramatic. Now, just as before, it's important to remember that this isn't something you feel directly. You don't experience space squeezing around you. Your immediate environment remains consistent. The interior of your spacecraft doesn't shrink. The objects around you don't distort, because everything inside your frame of reference contracts together, maintaining the same relationships. So there's no local change for you to observe. But when you look outward, toward distances that extend beyond your immediate environment, that's where the difference becomes clear. The path ahead shortens. The journey becomes, in a sense, more manageable, and this leads to an interesting outcome. From your perspective, you can travel vast distances in a shorter amount of time than someone at rest would expect. Not because you're breaking the speed limit, but because the distance itself has changed relative to you. It's as if the universe is meeting you halfway. Now, it helps to consider how this connects to what we discussed earlier about time. As your speed increases, your time slows relative to others. At the same time, distances along your direction of motion shrink. These two effects work together. They're not separate phenomena, but two sides of the same underlying structure. Space and time are linked, so when one changes, the other adjusts as well. Now, let's return to that distant star. From Earth's perspective, it might be several light years away. Even travelling at a significant fraction of the speed of light, the journey would take many years. But from your perspective, as you approach light speed, that distance contracts. What was once several light years might appear as a much shorter distance. So while your onboard clock continues ticking normally, the journey takes less time for you. You might reach that star in what feels like a few years, or even less, depending on your speed. Meanwhile, on Earth, much more time has passed. The two perspectives remain consistent. From Earth's point of view, the distance never changed. You simply travelled very quickly and your time slowed down. From your point of view, your time felt normal, but the distance you travelled was shorter. Both descriptions are valid. Both describe the same reality, just from different frames of reference, and that's the key to understanding length contraction. It's not that space itself is objectively shrinking, it's that measurements of space depend on the observer, just as measurements of time do. Now, there's something quietly fascinating about this idea. It suggests that distance, like time, is not absolute. It's not a fixed backdrop against which everything happens. Instead, it's something that can change depending on how you move, and that challenges another deeply held assumption. We tend to think of space as stable, solid, unchanging. But here, it reveals a flexibility that's usually hidden from us, a responsiveness to motion that only becomes apparent at extreme speeds. Now, consider how this would look from the outside. An observer on Earth watching your spacecraft would not see the distance to the star shrink. From their perspective, the distance remains the same. Instead, they would see your spacecraft taking a certain amount of time to reach it, with your onboard clock ticking more slowly. So again, each observer sees a different aspect of the same journey. You see the distance contract. They see your time dilate. Both observations are correct. They simply describe the same reality in different ways. Now, there's a subtle point here that's worth lingering on for a moment. When we say that distances contract along the direction of motion, we mean specifically along that direction. Distances perpendicular to your motion do not change in the same way. So the universe doesn't collapse uniformly around you. Instead, it compresses in one direction, the direction you're traveling. This creates a kind of directional effect. The path ahead shortens, the path behind stretches. But sideways, things remain largely unchanged. This contributes to the overall visual experience, which we'll explore more fully soon. But for now, it's enough to recognize that space itself is behaving differently depending on your motion. Now, imagine combining this with time dilation. Your time moves more slowly relative to others. Distances ahead of you shrink. Together, these effects create a powerful combination. They allow you to traverse vast stretches of space within a relatively short amount of your own time. From your perspective, the universe becomes more accessible, more compressed, more reachable. But from the perspective of those who remain behind, the journey still takes a long time. And that difference is what creates the separation we talked about earlier. You arrive having experienced less time. They remain having experienced more. Now, there's something almost comforting about the way these effects balance each other. Time stretches, space contracts. The universe adjusts itself in a way that preserves the fundamental limit set by the speed of light. Nothing breaks, nothing contradicts. Everything remains consistent within the framework of the laws that govern it. And yet, from our everyday perspective, it feels almost magical. The idea that distance itself can change, that the path to a destination can shorten depending on how you move. But this isn't magic, it's simply the natural consequence of a universe where space and time are deeply connected. A subtle change begins not with numbers or clocks, but with what your eyes are trying to make sense of. At first, it's easy to miss. The stars still shine. The darkness of space still stretches outward. Nothing suddenly breaks or collapses into something unrecognizable. But if you keep watching, if you let your gaze settle and adjust, you begin to notice that the view outside your window is no longer quite what it used to be. Not wrong, just different. Earlier, when your spacecraft was moving more slowly, the stars appeared scattered in all directions, a familiar pattern of distant points resting in the dark. Each one holding its place, unchanged, steady. But now, as your speed climbs higher and higher, approaching that extraordinary limit, the arrangement of those stars begins to shift. The ones in front of you, along your direction of travel, seem to draw inward, not moving closer in the usual sense, but gathering, compressing toward a central point. It's as though the entire forward view is being gently squeezed, funneled into a narrower and narrower region. At the same time, the stars behind you appear to spread out. They drift farther apart, stretching into a wider and softer pattern, as if the universe behind you is being gently pulled apart. This effect is known as relativistic aberration. It doesn't come from the stars themselves changing position, but from the way light reaches you when you're moving at such high speeds. Light that would normally arrive from the sides begins to tilt forward, bending into your direction of motion. So more and more of what you see appears to come from the space ahead of you. The result is a kind of visual narrowing. Your forward view becomes more concentrated, more intense. Your backward view becomes more diffuse, and everything to the side seems to drift toward the front. Now, this doesn't feel like a sudden distortion. It happens gradually, quietly, the kind of change you might only notice after watching for a while, when the difference between what was and what is becomes just noticeable enough to feel real. But that's only the beginning. because as your speed continues to increase, another layer begins to reveal itself: brightness. The stars ahead of you don't just cluster, they begin to glow more intensely. Their light becomes stronger, more concentrated, almost as if the universe is shining more brightly in the direction you're travelling. Meanwhile, behind you, things begin to dim. The light fades slightly. The stars lose some of their intensity, becoming softer, more distant in appearance. This contrast grows as your speed increases. Ahead becomes brighter, behind becomes darker, and the difference between the two becomes more pronounced. Now, there's a reason for this, one that connects directly to the way light behaves when there's relative motion between you and its source. But before we get into the details, it's worth simply sitting with the experience for a moment. Imagine looking forward and seeing the universe gather into a brighter, more focused region. Imagine turning around and seeing it stretch and soften behind you. It's not chaotic, it's not overwhelming, it's simply different. A gentle reshaping of what you see. Now, there's something else happening at the same time. The colours of the stars begin to shift. At first, this might be subtle. A faint change in hue. A slight adjustment in the tone of light. But as your speed increases further, the effect becomes more noticeable. Stars ahead of you begin to shift toward shorter wavelengths. Their light moves toward the blue end of the spectrum, and eventually beyond that. What was once visible light may begin to move into ultraviolet, or even X-rays, depending on how close you are to the speed of light. Meanwhile, the stars behind you shift in the opposite direction. Their light stretches toward longer wavelengths, redder, dimmer, eventually slipping out of the visible range altogether. So as you look behind, the universe may begin to fade, not because it's disappearing, but because its light is shifting beyond what your eyes can detect. And ahead, the universe becomes brighter, more energetic, more intense. Now this creates an interesting kind of imbalance. Your forward view becomes concentrated, bright and increasingly energetic. Your backward view becomes stretched, dim and eventually almost empty. It's not that the universe itself is changing, it's that your motion is altering the way light reaches you. And since everything you see depends on light, your perception of the universe changes with it. Now, there's one more subtle effect that begins to emerge. The sense of direction itself starts to blur. Because as more and more light is pulled into your forward view, the distinction between ahead and to the side becomes less clear. Light from the sides bends forward. Light from slightly behind may still reach you from the front. The universe, in a sense, wraps itself around your direction of motion. So instead of seeing a wide, evenly distributed field of stars, you begin to see something more concentrated, more focused, almost like looking through a lens that gathers everything into a central point. Now, it's important to remember that this doesn't feel disorienting in a chaotic way. Your brain adjusts, it interprets what it sees, and over time, this new view becomes your normal. Just as we adapt to changes in light or perspective in everyday life, you would adapt to this as well. But the difference remains. The universe no longer looks the way it did when you were at rest. It has taken on a new appearance shaped by your motion. Now, there's something quietly fascinating about this. The idea that what we see is not just a reflection of what exists, but of how we are moving, that the universe can appear differently depending on your state of motion. It reminds us that observation is not separate from experience, it's part of it. Now, as your speed continues to increase, these effects become more extreme. The forward view becomes more concentrated, more intense. The backward view fades further. Colours shift more dramatically. Brightness increases ahead, decreases behind. And all of this happens smoothly, continuously, without sudden jumps or breaks, just a gradual transformation. A question begins to take shape once the shifting stars and changing brightness settle into place. Not about speed, or time, or distance this time, but something more immediate. What would you actually see? Not in theory, not in equations, But in that quiet moment, sitting inside the spacecraft, looking out through the window, as you move faster than anything you've ever experienced before, because up to now, we've described how things change. Stars cluster, light grows brighter ahead and fades behind. Colours begin to shift. But what does that really look like, moment by moment, to your eyes? The answer is both simple and surprisingly unfamiliar. At lower speeds, even very high ones by everyday standards, the universe still looks much like it always has. Stars remain distinct points of light. Space is dark. The overall scene feels stable. But as your velocity continues to increase, approaching a significant fraction of the speed of light, the nature of what you see begins to change in a more noticeable way. The first thing you might become aware of is that the darkness of space is not quite as dark as it used to be. Ahead of you, that darkness begins to soften, almost as if it's being gently illuminated, not by a single source, but by the collective light of many distant stars, all being drawn into your forward view. That forward region becomes brighter, not blinding, not overwhelming, but steadily more luminous. The stars themselves, once scattered across a wide field, now appear closer together, their light overlapping slightly, blending into a more continuous glow. It's not that individual stars disappear, but their distinction begins to soften as their light becomes more concentrated. And then, as your speed increases further, something even more interesting happens. The light itself begins to change in character. Earlier, we touched on the idea that colours shift, but here, that shift becomes something you can actually notice. Stars ahead of you begin to appear bluer. At first, this might be subtle, a slight coolness in their colour, a gentle shift from warmer tones towards something sharper, more intense. But as your speed continues to climb, that shift grows stronger. Light that was once comfortably within the visible range begins to move beyond it. Ultraviolet, X-rays, even higher energy forms of radiation begin to dominate. Now, your eyes are not designed to see these wavelengths directly. So instead of perceiving them as new colours, you might experience them as an increasing brightness, or even as something difficult to interpret. The forward view could begin to feel almost washed in a kind of intense, featureless light, not because the stars have disappeared, but because their light has shifted beyond the range your eyes can easily process. Meanwhile, behind you, the opposite effect takes place. The stars that once filled the sky begin to redden. Their light stretches, becoming longer in wavelength. At first, this simply makes them appear warmer, softer. But as the effect increases, their light moves into infrared, beyond what your eyes can detect, and gradually they begin to fade. Not because they've gone anywhere, but because their light is no longer visible to you. So behind you, the universe begins to dim, not suddenly but gently. A slow fading of detail, a quiet retreat into darkness. And ahead of you, the universe becomes brighter, more concentrated, more intense. Now this creates a very particular kind of visual experience. Instead of seeing a balanced sky, with stars evenly distributed in all directions, you begin to see something more directional. The forward view becomes dominant, the sides contribute less, the rear fades away. It's as if your field of vision is being gently pulled forward, focused into the direction you're travelling. Now, there's another detail that becomes noticeable as your speed continues to increase. The shape of what you see begins to change. Not the physical shape of objects themselves, but the way they appear. Light from different parts of the sky arrives at slightly different times, and as your speed increases, these differences become more pronounced. This can create subtle distortions in how objects appear, especially those that are extended or closer than distant stars. But even here, the experience is not chaotic, it's smooth, gradual. Your brain continues to interpret the incoming light in a way that feels coherent. So rather than seeing something broken or fragmented, you perceive a continuous, if unfamiliar, view. Now, consider something else. At these speeds, the amount of light being concentrated into your forward direction becomes significant. Light that would normally be spread out across a wide area is now being gathered into a smaller region. This increases not just brightness, but intensity, energy. The light ahead of you carries more energy than it would if you were at rest, and while your eyes may not directly perceive that increase in energy as a new colour, it can still affect the overall appearance. The forward view may begin to feel sharper, more vivid, more intense, while the rear fades into softness and darkness. Now, there's a quiet balance here. Everything you see is still governed by the same underlying rules. Light still travels at the same speed. It still carries information from distant sources. But your motion changes how that information reaches you. And because your perception depends entirely on that incoming light, your experience of the universe changes with it. Now imagine sitting there, watching this transformation unfold. At first it's subtle, a slight brightening ahead, a gentle dimming behind. Then gradually, it becomes more pronounced. The universe begins to take on a new shape, a new balance. Not something alien or chaotic, but something different enough to feel meaningful. And yet, throughout all of this, your internal experience remains steady. Your thoughts move at the same pace. Your sense of time remains unchanged. Your body feels normal. It's only the view outside that evolves. And that contrast between the calm interior and the shifting exterior is part of what makes this scenario so fascinating. Now, there's one more aspect to consider before we move on. As the light ahead of you shifts into higher and higher energy ranges, it's not just a matter of visibility. It also raises questions about what kind of radiation is reaching your spacecraft, what kind of energy is interacting with it, and what that might mean for both the structure of the ship and your safety inside. But we'll come back to that in a little while. For now, it's enough to stay with the experience itself, looking out at a universe that no longer appears the way it once did. A forward view that grows brighter, more concentrated, more intense. A backward view that softens and fades. And a quiet realization that what you see is not just a reflection of what is out there, but of how you are moving through it. A familiar sound offers a gentle way into this idea. You've probably noticed how the pitch of a passing siren changes as it moves by. When it approaches, the sound feels sharper, higher, and once it passes, the tone drops, becoming deeper and more stretched out. Nothing about the siren itself has changed. It's still producing the same sound. But because of motion, the waves carrying that sound are compressed in front of it and stretched behind it. That simple effect, something most of us have heard countless times without thinking too much about it, turns out to have a direct connection to what happens with light at very high speeds. Because light, much like sound, also travels in waves, and when there is relative motion between you and the source of that light, those waves change. Not in speed. The speed of light always remains constant, but in how they are spaced, closer together or farther apart, and that spacing is what determines colour. Now, to ease into it, imagine once again that spacecraft moving forward, steadily increasing its speed. Somewhere ahead of you is a distant star sending out light in all directions. That light travels outward, wave by wave, each crest following the last at a regular spacing. If you were standing still, you would receive those waves exactly as they were emitted. The spacing between them would remain unchanged, and you would perceive the star's natural colour. But you're not standing still. You're moving toward that star, and as you do, something subtle begins to happen. You begin to encounter each incoming wave a little sooner than you would if you were at rest. So instead of receiving the waves at their original spacing, you receive them slightly closer together, compressed. And when light waves are compressed, their wavelength decreases. Shorter wavelengths correspond to higher frequencies, and higher frequencies correspond to bluer light. So the star ahead of you begins to shift toward blue. At first, the effect is gentle, a slight cooling of its colour. But as your speed increases, the compression becomes more pronounced. The wavelengths shorten further, the colour shifts more dramatically, eventually moving beyond visible blue into ultraviolet. And beyond that, into forms of radiation your eyes cannot directly perceive. Now, turn your attention behind you. There are stars there as well, sending their light outward just as before, but now you are moving away from them. And in this case, the opposite happens. Each successive wave takes a little longer to reach you. The spacing between them stretches, and when light waves are stretched, their wavelength increases. Longer wavelengths correspond to lower frequencies, and lower frequencies correspond to redder light. So the stars behind you begin to shift toward red. At first, it's subtle, a warm tint, a softening of colour. But as your speed increases, the stretching becomes more pronounced. The wavelengths grow longer. The light shifts further into the red, then into infrared, and eventually beyond what your eyes can detect at all. So behind you, the stars begin to fade, not because they're disappearing, but because their light is no longer within the range your eyes can see. Now this effect, the shifting of light due to motion, is known as the Doppler effect, and it applies not just to sound, but to all kinds of waves, including light. But at everyday speeds, the effect is usually too small to notice with light. You don't see colours shifting as cars drive past or as you move through a room. But at speeds approaching that of light, the effect becomes significant, and then unavoidable. Now there's something quietly fascinating about this, because it means that colour itself is not entirely fixed. It's not just a property of the object emitting the light. It's also influenced by how you are moving relative to that object. So two observers moving differently could see the same star as different colours. One might see it as white. Another, moving toward it at high speed, might see it as blue or even beyond visible light. And both would be correct. Each is observing the light as it reaches them, shaped by their motion. Now, return to the view from your spacecraft. As your speed continues to increase, the forward region of space becomes dominated by this blue shift. Light compresses, frequencies rise. The view ahead becomes brighter, sharper, more energetic. Meanwhile, behind you, the red shift grows stronger. Light stretches, frequencies drop. The view softens, dims, and eventually fades into darkness. And this creates a kind of visual imbalance, a universe that appears concentrated ahead and diminished behind. Now, there's an interesting detail here that connects to what we discussed earlier. The Doppler effect doesn't act alone. It works together with the clustering of light we described before, the way light from different directions is drawn forward. So not only is the light ahead of you compressed and shifted toward higher energies, but more of it is being gathered into your forward view. This amplifies the effect, making the forward region even brighter, even more intense, while the rear becomes quieter, darker, more distant. Now imagine watching this over time. The stars ahead slowly shifting colour, white becoming blue, blue becoming something beyond, the stars behind fading, slipping out of view, and all of it happening smoothly, gradually, without any sudden transitions. Now, there's another layer to consider. As light shifts into higher frequencies, it carries more energy, so the blue shifted light ahead of you isn't just different in colour, it's more energetic, more intense, and that has implications not just for what you see, but for how that light interacts with your spacecraft. But we'll explore that more carefully a little later. For now, it's enough to stay with the visual experience. A universe where colour is no longer fixed, where motion reshapes what you see, where the same stars can appear differently depending on how fast you're moving and in which direction. And there's something quietly humbling about that. The realization that even something as simple as colour, something we often take for granted, is not absolute. It depends on perspective, on motion, on the relationship between you and the light reaching your eyes. Now, as your speed continues to increase, these effects become more extreme. The forward view becomes dominated by higher and higher frequencies. The rear fades further into invisibility, and the overall appearance of the universe continues to evolve. Long before anything breaks or becomes visually overwhelming, there's a quieter obstacle that begins to take shape. Not something you can see through the window, and not something you would directly feel inside the spacecraft, but something that steadily grows in the background. Energy. Not just fuel in the ordinary sense, not simply how much you've packed into tanks or stored in some advanced system, but the deeper question of how much energy it takes to keep accelerating as your speed increases. At low speeds, the relationship feels simple. If you want to go faster, you apply more energy. Push a little harder, you move a little faster, double the effort, and your speed increases accordingly. It's predictable, almost intuitive, something that matches everyday experience. But as your spacecraft continues its journey, climbing to higher and higher speeds, that simple relationship begins to change. At first, the difference is subtle. You apply more energy, and your speed increases just as expected. But the increase is slightly less than it would have been at lower speeds. It's a small discrepancy, easy to overlook. Then, as you push further, it becomes more noticeable. Each additional burst of energy produces a smaller increase in speed than the one before. The pattern shifts. You're still accelerating. You're still going faster. But the returns begin to diminish, and as your velocity approaches a significant fraction of the speed of light, this effect becomes impossible to ignore. You can keep adding energy, but your speed increases by smaller and smaller amounts. It's like climbing a hill that gradually steepens. At first, the incline is gentle, then it becomes steeper, then steeper still, and eventually it feels as though no matter how much effort you apply, you're barely gaining any height at all. Now, this isn't due to friction. It's not because space is resisting you in the way air resists a moving object. Instead, it's something more fundamental. The way energy relates to motion begins to shift. More and more of the energy you put into the spacecraft stops contributing to its speed in the way you expect. Instead, it goes into something else, into increasing its resistance to further acceleration. From an outside perspective, it's as if the spacecraft is becoming more and more difficult to push. Heavier, in a sense. Not because its actual mass is increasing in the way we usually think about it, but because its behaviour begins to resemble that of something with greater mass. So each additional unit of energy has less effect on its speed, and this trend continues. The closer you get to the speed of light, the more extreme it becomes. Now imagine trying to reach that final step, that last fraction of speed. You add more energy, then more again, and each time your speed increases just a little less than before, until eventually the amount of energy required to gain even the smallest additional increase becomes enormous. And then, beyond enormous, it grows without bound, which leads to a conclusion that feels almost inevitable once you see it clearly. Reaching the speed of light would require an infinite amount of energy, not just a lot, not an unimaginably large amount, but truly infinite. And that's where the path ends, because no physical system can supply infinite energy. No matter how advanced your technology becomes, no matter how efficient your engines are, that requirement cannot be met. It's not a practical limitation, it's a fundamental one. Now, from inside the spacecraft, you wouldn't directly feel this growing demand for energy. You wouldn't sense the equations tightening or the limits approaching. Your experience would remain smooth, continuous, calm. But behind the scenes, the effort required to continue accelerating would be increasing dramatically. Each additional gain in speed would come at a greater and greater cost. Now, there's another layer to this that connects back to what we discussed earlier. As your speed increases, your time slows relative to others. Distances ahead of you contract. The universe adjusts in subtle ways, and all of these effects are tied together. They're not separate phenomena, they're part of a single consistent framework. So the energy problem isn't isolated, it's connected to the way space and time behave. The closer you get to the speed of light, the more extreme those changes become, and the more energy is required to sustain that state. Now consider what this means for your journey. At moderate speeds, even very high ones, the energy required is manageable in principle. Difficult, yes, but not fundamentally impossible. But as you push closer to the speed of light, the demands grow rapidly, and eventually they become insurmountable. So while you can approach the speed of light, getting closer and closer, you can never quite reach it. There will always be a gap. A small one, perhaps, but a gap that cannot be closed. Now, there's something quietly elegant about this. The universe sets a limit, not by placing a barrier in your path, but by shaping the relationship between energy and motion. It doesn't stop you directly. It simply makes it impossible to take that final step. Now, there's another aspect to consider. As your speed increases and the energy required grows, the energy carried by the light around you also begins to play a more significant role. Earlier we spoke about how light ahead of you becomes blue shifted, moving into higher frequencies. Higher frequencies mean higher energy. So the light you encounter in the forward direction becomes more energetic, more intense. And at extreme speeds, this can become a practical concern, because that incoming radiation carries energy that can interact with your spacecraft, with its structure, with anything inside. But again, we'll explore that more carefully in a moment. For now, it's enough to recognize that energy is not just something you use to move. It's something that shapes what is possible, and as you approach the speed of light, it becomes the limiting factor. Now imagine continuing this journey, adding more energy, pushing harder, watching your speed increase, but by smaller and smaller amounts, the curve flattening, the progress slowing, until eventually it becomes clear that no matter how much more you add, you will never quite reach that final value, and that realization changes the way you think about the goal. It's no longer about reaching the speed of light, it's about understanding what happens as you get close, because that's where the interesting effects take place. That's where time slows, distances shrink, the universe changes its appearance, and your experience begins to diverge from that of everyone else. If reaching the speed of light is impossible, what would it mean if you somehow could? What would happen at that exact limit? What would time look like? What would space become? And is it even meaningful to ask that question? There comes a point in this journey where the idea of more quietly stops behaving the way we expect it to. More speed, more energy, more effort. Up to a certain stage, everything feels manageable, at least in principle. You add energy, and your spacecraft responds. You accelerate, and your speed increases. The relationship feels familiar, even if the numbers involved are far beyond anything we've ever achieved. But as that speed creeps closer and closer to light itself, something begins to change in a way that is not just noticeable, but fundamental. The curve stops being friendly. It begins to turn, not sharply, not abruptly, but in a way that becomes increasingly difficult to ignore. Each new increase in speed demands more energy than the last, and not just slightly more, but disproportionately more. At first, this feels like an inconvenience. Then it starts to feel like a challenge, and eventually it reveals itself as something much deeper, a limit that cannot be crossed. Now it helps to picture this not as a wall, but as a slope. Imagine walking uphill. At the beginning, the incline is gentle. Each step takes effort, but it's manageable. You can keep going without too much difficulty. As you continue, the slope becomes steeper. Each step requires more energy. You slow down slightly, but you're still making progress. Then the incline grows sharper still. You lean forward, you push harder. Each step becomes more demanding. And then, at some point, the slope becomes so steep that no matter how much effort you apply, you can barely move upward at all. Not because you've stopped trying, but because the nature of the slope itself has changed. That's what the infinite energy barrier is like. It's not a sudden stop. It's a gradual tightening, a curve that becomes steeper and steeper until forward progress, at least toward that final limit, becomes impossible. Now, in the context of your spacecraft, this slope is defined by the relationship between energy and speed. At low speeds, adding energy increases your speed in a fairly direct way. At higher speeds, that relationship begins to shift, and as you approach the speed of light, it transforms entirely. The energy required to increase your speed begins to rise more and more rapidly. At first, it's manageable, then it becomes significant, then enormous, and eventually it grows without bound. Which brings us to the key realization. To reach the speed of light, you would need an infinite amount of energy, not just more than we currently have, not just more than we could realistically produce, but literally infinite. And that's where the idea of a barrier comes from. Not a physical wall you could crash into, but a limit defined by the structure of the universe itself, a point beyond which the requirements become impossible to satisfy. Now, from inside the spacecraft, you wouldn't feel this barrier in any dramatic way. There would be no sudden resistance, no force pushing back against you. Your experience would remain smooth, continuous. But the effort required to continue accelerating would grow more and more extreme. Your engines would need to produce greater and greater amounts of energy for smaller and smaller gains in speed. And eventually, no matter how advanced your technology, you would reach a point where further acceleration becomes effectively impossible. Now, there's something quietly fascinating about this, because it means that the speed of light is not just a limit in the sense of we haven't reached it yet. It's a limit in the sense that it cannot be reached. Not by anything with mass, not by any object that exists in the way we do. And that raises an interesting question. Why? Why does the universe impose this particular restriction? Why does it allow us to approach the speed of light, to get closer and closer, but never quite reach it? The answer lies in the way energy, mass, and motion are connected. As an object moves faster, its resistance to acceleration increases, not in a simple, linear way, but in a way that becomes more pronounced the closer it gets to the speed of light. From the outside, it behaves as though it's becoming more massive, not because it's gaining more material, but because it becomes harder to change its motion, so each additional push requires more energy, and that requirement grows faster than your speed does. Now imagine trying to close the final gap. You're already moving at 99% of the speed of light. You add more energy, your speed increases slightly. Now you're at 99.9%. You add even more energy. Your speed increases again, but by an even smaller amount. 99.99%, and so on. Each step brings you closer, but each step also requires dramatically more energy than the last, until eventually, the amount of energy required to reach the next fraction becomes so large that it effectively becomes unreachable, and beyond that, infinite. Now, there's something almost paradoxical about this. You can always get closer. You can approach the speed of light as closely as you like, in principle, but you can never actually reach it. There will always be a gap, a tiny one perhaps, but one that cannot be eliminated, and that gap is what preserves the structure of the universe. Because if objects with mass could reach or exceed the speed of light, something else would begin to break down. Cause and effect, the order of events, the consistency of time itself. At speeds beyond light, the equations that describe motion begin to produce results that don't align with our understanding of reality. Events could appear to happen out of order. Signals could arrive before they are sent. The sequence of cause and effect could become scrambled. So the infinite energy barrier does more than limit speed. It protects the consistency of the universe. It ensures that there is a maximum rate at which information, influence, and causality can propagate. Now, there's another way to think about this that feels a little more intuitive. Imagine that the universe has a kind of built-in pacing, a maximum tempo at which events can unfold. The speed of light sets that tempo. Everything else must move within it. You can speed up, you can approach that tempo, but you cannot exceed it, because doing so would disrupt the rhythm that keeps everything in order. Now, from your perspective inside the spacecraft, this limit doesn't feel like a restriction. It doesn't prevent you from experiencing time, or moving through space, or observing the universe. It simply shapes the way those experiences unfold. You can travel vast distances. You can experience time differently from others. You can see the universe change in remarkable ways. all without ever reaching that final boundary, and that's what makes the journey itself so interesting. The effects we've been exploring, time dilation, length contraction, the shifting of light, all occur as you approach the speed of light. Not the limit, but near it. So the barrier doesn't take anything away from the experience, it defines it. Now there's one more detail worth considering. If reaching the speed of light requires infinite energy, then anything that already moves at that speed must exist in a fundamentally different way. And that brings us back to light itself. Photons, the particles of light, have no mass. And because they have no mass, they don't face the same restriction. They don't need infinite energy to move at light speed. They simply do, always, from the moment they are created. And that raises an interesting question. If something can exist at the speed of light, what does that mean for its experience of time? Does time pass for it at all? Or does it experience something entirely different? It's tempting at this stage to lean just a little further into the question. Not what is possible, not what the equations allow, but what if somehow you crossed that final threshold anyway? What if all the limitations we've been carefully building up, the rising energy, the resistance, the infinite barrier, could be set aside just for a moment? What would it actually be like? Because even though physics tells us this situation cannot happen for anything with mass, imagining it still reveals something important. It lets us explore the very edge of how the universe behaves, where familiar ideas begin to lose their meaning. So for a moment, gently, we set aside the restriction. Your spacecraft continues to accelerate. Closer, closer still. 99% of light speed, 99.9, 99.99. Each step smaller than the last. And then, somehow, you reach it. Not approach it. Not hover just below it. But arrive at that exact speed. And this is where something very unusual happens. Because the moment you try to describe what it's like, the usual language begins to slip. The concepts we've been using, time passing, distance existing, even motion itself begin to lose their footing. Let's start with time. As we've already seen, the faster you go, the slower your time passes relative to others. Closer to light speed, your time slows dramatically. From an outside perspective, your clock ticks more and more slowly. So what happens at the limit? At the exact speed of light, the equation suggests that time, from the perspective of an external observer, would stop entirely for you. Not slow to a crawl, not stretch into long intervals, but stop. Your clock would no longer tick. Events inside your spacecraft would appear frozen. But that's only one side of the story. Because from your own perspective, the idea of time stopping doesn't quite make sense. You can't experience no time passing. Experience itself requires time. Thoughts unfold over time. Perception happens over time. Without time, there is no sequence of events, no before or after. So what would you actually experience? The answer is nothing in the usual sense. Because at light speed, the idea of a frame of reference, a viewpoint from which you can describe your own experience, begins to break down. The rules we've been using no longer apply, and that's the key point. Reaching the speed of a light doesn't just change your experience. It removes the framework that allows experience to exist in the way we understand it. Now, let's turn to distance. Earlier, we saw that as your speed increases, distances in the direction of motion contract. They become shorter from your perspective, closer. So what happens at the limit? At the speed of light, the equation suggests that the distance between your starting point and your destination collapses to zero. Not small, not reduced, but zero, which leads to a strange conclusion. From the perspective of something moving at light speed, the journey between any 2 points happens instantly. No time passes, no distance exists. The start and the end are, in a sense, the same. Now that doesn't mean the universe itself collapses. From the outside, everything continues as normal. Distances remain, time flows. But from the perspective of something at light speed, those distinctions disappear. Now, try to hold those two ideas together. Time stops. distance collapses, and suddenly the concept of travel itself becomes difficult to define, because travel requires both time and distance, a path, a duration, a sequence of movement. But here, those ingredients are no longer available. So what does it mean to move at light speed? In a very real sense, it means that the usual idea of movement no longer applies. It's not that you move very quickly from one place to another, it's that the distinction between those places disappears within your frame of reference. Now, there's something quietly profound about this. The speed of light isn't just a fast speed, it's a boundary where the structure of space and time itself changes in a fundamental way, a point where our everyday concepts stop working. Now, there's another way to approach this that may feel a little more intuitive. Think about how we experience motion at normal speeds. You start in one place, you move, time passes, you arrive somewhere else, there's a clear sequence, but at light speed that sequence collapses. There is no during, only something more like a connection between events. Now, it's important to remember that this is not something we can directly experience, because anything with mass cannot reach this state, so when we talk about what it would be like, we're stepping into a kind of conceptual space, a way of exploring the limits of our understanding, and in that space the answer is less about sensations and more about structure. Time ceases to behave as a dimension you move through. Distance ceases to behave as something you cross. Instead, events become directly linked. Now, this might sound abstract, but it has a very concrete counterpart. Light itself, photons, they always travel at the speed of light. They don't accelerate to it, they don't approach it. They exist at that speed from the moment they are created. And according to the equations of relativity, if you could somehow describe the experience of a photon, it would not involve time in the way we understand it. From emission to absorption, the journey would be instantaneous, not because it happens quickly, but because time does not pass in that frame. Now again, it's important to be careful here. We don't say that photons have experiences, the concept doesn't apply in the same way, but mathematically, this is what the description suggests, and it gives us a glimpse of what the limit represents. Now, let's return briefly to your spacecraft. If, somehow, it could reach the speed of light, it would no longer behave like an object moving through space and time in the usual way. Its internal processes, its clocks, its structure, all depend on time. Without time, those processes cannot unfold. So the idea of a functioning spacecraft at light speed becomes inconsistent, not just difficult, but undefined. And that's why the infinite energy barrier exists. It's not just preventing you from going faster, it's preventing you from entering a regime where the usual rules no longer support the existence of objects with mass. Now, there's something quietly reassuring about that. The universe sets limits that preserve consistency, that keep the structure of reality intact. Even if those limits feel restrictive, they serve a purpose. Now, there's one final thought to rest with for a moment. The speed of light is not just a maximum speed. It's a boundary between different kinds of existence. On one side, objects with mass, moving through time, experiencing duration. On the other, massless particles existing at that limit, where time and distance behave in entirely different ways. And while we cannot cross that boundary ourselves, we can approach it. We can explore its effects. We can understand how the universe behaves as we get closer. And in doing so, we gain insight into something deeper. Not just how fast things can go, but how space and time themselves are woven together. Light leaves a star quietly. No announcement, no fanfare, just a release. A tiny packet of energy slipping away from its source, beginning a journey across space that might last seconds or years, or millions of years depending on where it's headed. We usually imagine that journey the way we imagine our own. A beginning, a middle, an end. Travelling across distance, taking time to arrive. But when we turn our attention toward the photon itself, the particle of light making that journey, something unusual begins to happen, because the way we describe motion, time and distance doesn't quite apply in the same way anymore. Now, it's important to move carefully here. When we say the perspective of a photon, we're using language in a slightly relaxed way. Photons don't have awareness. They don't observe or experience anything in the sense that we do. But we can still ask a meaningful question. If we try to describe what happens along the path of a photon using the same ideas we use for ourselves, what do we find? And the answer is surprisingly minimal. Let's begin with time. Earlier, we saw that as an object moves faster and faster, its time slows relative to others. Closer to the speed of light, that slowing becomes extreme. So what happens at the speed of light itself? The equations of relativity suggest that along the path of a photon, no time passes. Not a small amount, not a stretched out version of time, but none at all, which leads to a curious conclusion. From the moment a photon is emitted to the moment it is absorbed, there is no passage of time along its path. No duration, no sequence. Now, that doesn't mean that from our perspective the journey is instantaneous. Light from the sun takes about 8 minutes to reach Earth. Light from distant stars can take years, centuries or longer. From our point of view, that time is very real. But along the photon's path, the concept of elapsed time doesn't apply. It's as if the beginning and the end are directly connected. Now, let's turn to distance. As we've seen, distances contract along the direction of motion as speed increases. So what happens at light speed? The equation suggests that, along the photon's path, the distance between where it is emitted and where it is absorbed collapses to zero. Not small, not reduced, but effectively non-existent. So now, hold those two ideas together. No time passes, no distance exists along the path. And suddenly, the idea of a journey begins to lose its meaning. Because a journey requires both time and distance, a path to cross, a duration over which it unfolds. But here, those elements are no longer present in the usual way. Now again, this doesn't mean that photons are experiencing anything. It means that when we apply the framework of relativity to something moving at the speed of light, the quantities we use to describe motion behave very differently. Time and distance, which feel so fundamental to us, become less relevant in this context. Now, there's something quietly profound about this. It suggests that the universe can be described in different ways depending on how you move. For us, moving at everyday speeds, time flows, distances remain fixed, events unfold in sequence. But for light, those concepts are arranged differently. Now, consider what this means for the idea of connection. A photon can be emitted from a distant star, travel across the vast emptiness of space, and eventually be absorbed by your eye. From your perspective, that journey took years, perhaps millions of years. But from the photon's point of view, if we can use that phrase carefully, there is no separation between those events. Emission and absorption are directly linked. No time passes between them, no distance separates them, and that gives light a very special role in the structure of the universe. It acts as a kind of connector, a bridge between events, carrying information from one place to another, but doing so in a way that doesn't involve time or distance in the usual sense. Now this might feel a little abstract, so let's bring it back to something more tangible. Imagine looking at a distant star. The light reaching your eyes left that star long ago. It travelled across space, carrying information about that star's state at the moment it was emitted. From your perspective, that information has taken time to arrive. But the photon itself doesn't experience that delay. It simply connects the two events. Now, there's an interesting implication here. If you could somehow step into the frame of a photon, which again is not physically possible for anything with mass, you would not see a universe unfolding over time. You would not perceive motion. You would not observe events happening in sequence, because those concepts rely on the passage of time. Instead, you would have something more like a direct mapping between events. But here, language begins to struggle. because our words are built around experiences that involve time and sequence. Without those, it becomes difficult to describe what remains. Now, this is one of the reasons why the speed of light is such a special boundary. It marks the point where our usual way of describing the world begins to break down, where the concepts we rely on, time, distance, motion, need to be reinterpreted. And that's why nothing with mass can reach this speed, because objects with mass require time to exist in the way we understand. Their internal processes depend on it. Without time, those processes cannot unfold. Now, there's something quietly elegant about the way this all fits together. The speed of light is not just a limit, it's a boundary between different kinds of behaviour. On one side, objects with mass, moving through time, experiencing duration. On the other, massless particles, existing at that boundary, where time and distance behave in fundamentally different ways, and light sits exactly at that boundary, always moving at that speed, always connecting events across space. Now, as we return to your spacecraft, still travelling at speeds approaching this limit, it becomes clear why you can get close, but never quite reach it. Because crossing that boundary would require a fundamental change in how you exist, a shift from something that experiences time to something that does not. And that's not something a spacecraft or a person can do. Now, there's one more detail to consider. Even though photons don't experience time in the usual sense, they still play a crucial role in how we experience the universe. They carry light, they bring us information, they allow us to see. Without them, the universe would be dark, silent, disconnected. So while their perspective, if we can call it that, is very different from ours, their presence is essential to our own experience. They connect us to distant places, to distant times, to events far beyond our immediate surroundings, and in doing so, they remind us that the universe is not just a collection of objects, but a network of connections. A strange kind of question begins to form once you linger long enough at that boundary. Not about speed this time, not about distance, not even about what you would see, but something much more fundamental. Does time even exist there at all? It sounds almost like one of those late-night thoughts that circles around quietly, the kind that feels simple at first and then becomes harder to pin down the more you look at it. Because up to now, we've been treating time as something that changes. It slows down, it stretches, it behaves differently depending on motion, but it's still there, still flowing, still something you move through, but at light speed that idea begins to loosen. Not gradually, not in the same gentle way as before, but in a way that feels more like it's slipping out of reach. Earlier we touched on the idea that along the path of a photon no time passes. Now, it's worth staying with that for a moment, not rushing past it because it's easy to hear it and think of it as just another unusual detail. But it's more than that. It changes the role that time plays entirely. For us, time is inseparable from experience. Everything we do, everything we perceive, unfolds across it. A thought begins, continues, and ends. A moment leads to another. There's always a sense of sequence. But if no time passes, then that sequence has no place to exist. There is no before, no after, no unfolding. Now, from our perspective, looking at light travelling across space, we still measure time. We still say it takes 8 minutes to travel from the Sun to Earth. We still observe duration, so time clearly exists in that sense. But that's from our frame of reference, from within the structure of our own motion. When we shift our attention to the limit itself, the speed of light, the framework changes, and within that framework, time, as we usually define it, doesn't behave in the same way. Now, this doesn't mean that time disappears from the universe. It means that for something moving at that exact speed, the concept of time doesn't apply in the usual sense, and that distinction is important. Because it's not that time stops everywhere, it's that time is not something that can be meaningfully assigned along that path. Now, there's a useful way to approach this that keeps things grounded. Instead of asking whether time exists in an absolute sense, we can ask how time is measured. Time is always measured along a path. A clock follows a path through space and time, and its ticking reflects how much time has passed along that path. For objects with mass, those paths always include time. They move forward through it. But for light, the situation is different. The path that light follows through space-time does not include the passage of time in the same way. So when we ask whether time exists at light speed, what we're really asking is whether a clock travelling at that speed would tick. And the answer, according to relativity, is no. There would be no ticks, no intervals, no duration. Now, that leads to a curious realization. If there is no passage of time along that path, then events connected by that path are not separated by time in the way we usually think. The emission of a photon and its absorption are not separated by a duration along that path. They are directly linked. Now, this can feel a little unsettling because it challenges our sense of how the world works. We're used to thinking in sequences. This happens, then that happens, cause, then effect. But here those ideas begin to blur, not because they stop being meaningful in general, but because at this boundary, the structure that supports them is different. Now, it's important to keep something in mind. We cannot step into this frame of reference. Anything with mass cannot reach the speed of light. So this isn't something we can experience directly. It's something we understand through the structure of the equations that describe the universe, and through careful experiments that confirm how time behaves as we approach that limit. Now, there's another way to think about this that may feel a little more intuitive. Consider how we define a moment. A moment is usually thought of as a point in time, but it still belongs to a sequence. It still sits between what came before and what comes after, but at light speed there is no sequence along the path, so the idea of a moment becomes something else. Not a point in a timeline, but more like a connection between events. Now, again, this is where language starts to struggle. Because our words are built around experiences that involve time, we describe things as happening, changing, unfolding. But here, those verbs lose their usual meaning. Because without time, there is no unfolding. Now, there's something quietly profound in that. The idea that time is not a universal background that exists independently of everything else. Instead, it depends on motion, on the path you take through the universe. For us, moving at everyday speeds, time feels steady, reliable, always present. But at the boundary defined by the speed of light, that presence fades, not in a dramatic way, but in a way that reveals something deeper. That time is not a fixed stage on which events play out. It's part of the structure of those events. Now, this leads to an interesting philosophical question. If time does not pass along the path of light, then what does that say about the nature of time itself? Is it something fundamental, or is it something that emerges from the way we move through the universe? Some physicists suggest that time may not be a fundamental ingredient of reality, that it might arise from more basic relationships between events, from change, from interaction, from the way systems evolve, and that at certain limits, like the speed of light, that structure reveals itself. Now, this doesn't mean that time is an illusion in the everyday sense. It doesn't mean that your experiences are somehow unreal. Time is very real in the context of how we live. It shapes everything we do. But it may not exist in the same way at every level of description. And that's what this boundary shows us. Now, returning to your spacecraft, still travelling just below that limit, you remain within the realm where time exists, where your clock ticks, where your thoughts unfold, where moments follow one another. You never cross into that timeless boundary, but you approach it, and as you do, you see its effects. Time slows relative to others, distances shrink, the universe changes its appearance, all pointing toward that limit. Now, there's something almost reassuring about this. The universe allows us to explore these effects, to approach the boundary, to understand how reality behaves near it. But it doesn't allow us to step beyond it, because beyond it, the concepts that support our existence no longer apply in the same way. Now, there's one final thought to rest with here. When we ask whether time exists at light speed, we're really asking about the limits of our own understanding, about how far our concepts can stretch before they need to be redefined. And in that sense, the answer is both simple and complex. Time exists in the universe, but not in the same way for everything. And at the speed of light, it becomes something that no longer behaves as a flowing dimension. Instead, it becomes something that depends entirely on perspective, on motion, on the path you take. Most of what we rely on to understand the world was built slowly, quietly, through ordinary experience. You move through a room and the room stays the same size. You watch a clock and it ticks at a steady pace. You look at the sky and the stars hold their positions. Over time, these patterns become expectations, not something you actively think about, but something you trust without needing to question it. Space feels fixed. Time feels universal. Events seem to unfold in a clear, shared order, and for most situations that works perfectly well. But as this journey has been gently revealing, those expectations begin to loosen once you move into the realm of very high speeds. Not all at once, not in a way that feels chaotic, but in a way that steadily separates what feels intuitive from what is actually happening. This is where relativity becomes more than just a set of equations. It becomes a reminder that our intuition is shaped by a very limited slice of reality. Now consider something simple. Two events happening at the same time, in everyday life, that feels straightforward. If two lights flash at the same moment, you expect that to be true for everyone observing them. But in relativity, that assumption doesn't always hold. If someone is moving relative to those events, they may not agree on whether the flashes happened at the same time. From one perspective, they are simultaneous. From another, one happens before the other, and neither perspective is more correct than the other. Each is valid within its own frame of reference. Now that's not something we ever encounter in daily life. Speeds are too low, the differences are too small to notice, so our intuition settles into a simpler model. Time is shared. Events are ordered the same way for everyone, but relativity shows us that this model is only an approximation, a useful one, but not a complete one. Now, let that idea sit for a moment. Two observers, both correct, both describing the same pair of events, but disagreeing on their order. It doesn't feel wrong exactly, but it doesn't feel comfortable either, because it challenges something very basic. The idea that there is a single, universal timeline. Now this connects directly to what we've been exploring. As your spacecraft moves faster and faster, your experience of time begins to diverge from that of others. Clocks no longer agree, durations no longer match, and the sequence of events can begin to look different depending on how you're moving. Now, there's another layer to this that adds to the sense that intuition is slipping. Length contraction. From your perspective, distances ahead of you shrink. From someone at rest, they remain the same. Again, both descriptions are valid, but they don't align in the way our everyday experience would suggest. So space itself, which feels so stable and reliable, becomes something that depends on motion. Now imagine trying to hold all of this together at once. Time is not universal. Distance is not fixed. Simultaneity is not absolute. Each observer carries their own version of these quantities shaped by their motion, and yet everything remains consistent. No contradictions, no breakdown in the laws of physics, just a deeper structure that accommodates all of these perspectives. Now, there's a reason this feels difficult to grasp. Our intuition is built from experience at very low speeds compared to the speed of light. In that regime, the differences between these perspectives are so small that they can be ignored. Time appears universal. Space appears fixed. Simultaneity appears absolute. So our brains learn a simplified version of reality, one that works well enough for everyday life. But when we move into the domain of high speeds, that simplification begins to break down, and we're left with a choice. Either hold on to intuition and reject the results, or let intuition stretch and adapt. Now, what's interesting is that relativity doesn't ask us to abandon intuition entirely. It asks us to refine it, to replace the idea of absolute time with the idea of proper time, the time experienced along a particular path, to replace fixed distances with distances that depend on motion, to replace a single timeline with a network of timelines, each tied to an observer. Now, there's something quietly elegant about this. Even though it feels less familiar, it's actually more consistent. It accounts for all observers. It preserves the laws of physics in every frame of reference. And it explains the effects we've been describing without contradiction. Now, let's return briefly to your spacecraft. Inside, everything still feels normal. Your clock ticks, your thoughts unfold, your environment behaves as expected. But when you compare your experience to someone else's, the differences emerge. Time has passed differently, distances have behaved differently, events may not line up in the same way. And yet, neither perspective is privileged, neither is more real. They are simply different views of the same underlying reality. Now there's one more aspect to consider: causality, the order of cause and effect. Even though relativity allows for differences in how events are ordered in time, it preserves causality. An effect cannot occur before its cause in any valid frame of reference. This is maintained by the structure of spacetime itself, and the speed of light plays a key role in that. It sets the maximum speed at which information and influence can travel. So while intuition about time and space may break down, the deeper consistency of cause and effect remains intact. Now, that's an important anchor, because it means that even in this more complex picture, the universe remains coherent. Events still relate to each other in a consistent way. Now, there's something quietly reassuring in that. Even as our intuitive picture dissolves, the underlying structure holds. That intuition is not wrong, it's just limited. It works within a certain range, and beyond that range, it needs to expand. Now, we'll begin to turn toward a more practical question. Even if we can't reach the speed of light, could we get close? How close could we realistically come? What would it take? And what would that mean for a real spacecraft, a real journey, a real attempt to approach that limit? Not reach the speed of light, we already understand why that isn't possible. But approach it in a meaningful way. Build something, launch it, and let it travel fast enough for these effects to become more than just equations. Because there's a difference between understanding something and experiencing it, even indirectly. Now, the first thing to recognize is that we've already taken very small steps in this direction. Particles in accelerators, tiny fragments of matter, have been pushed to speeds extremely close to that of light. Inside facilities like CERN, protons are accelerated to over 99.999% of light speed. And when that happens, all the effects we've been discussing are not just theoretical. Time dilation is measurable. Their internal process is slow relative to ours. Their behavior matches the predictions of relativity with extraordinary precision. So in that sense, we already know it's possible to approach light speed. But there's an important difference. Those particles are incredibly small. They carry no passengers, no structure that needs to remain intact over long periods. Scaling that up to something like a spacecraft introduces an entirely different set of challenges. Now imagine what it would take. To accelerate a human-sized vehicle to even a fraction of light speed, say 10% or 20%, requires an enormous amount of energy, far beyond anything we currently produce for a single object. And as we've seen, the closer you get to light speed, the more rapidly that energy requirement grows. So even reaching, say, 50% of light speed would be an extraordinary achievement. Now there are ideas, concepts that scientists and engineers have explored not as immediate plans, but as possibilities. One of them involves using light itself as a source of propulsion, a concept often referred to as a light sail. Instead of carrying fuel, a spacecraft could be pushed forward by an intense beam of light, perhaps from powerful lasers stationed far away. Projects like Breakthrough Starshot have explored this idea, proposing tiny, lightweight probes that could be accelerated to a significant fraction of light speed using directed energy, not carrying people, not even carrying large instruments, just small, efficient payloads designed to travel quickly and send information back. Now, even in these concepts, the speeds being considered are still well below the speed of light, perhaps 10%, maybe 20%, enough to reach nearby stars within decades rather than thousands of years, and even that is incredibly ambitious, because maintaining stability, protecting the spacecraft from radiation, and ensuring communication across such distances all present major challenges. Now consider what happens as you push beyond that, toward 50%, 70%, 90%. The energy requirements grow dramatically, the engineering challenges multiply, even tiny particles of dust in space, harmless at low speeds, become dangerous at high velocities. At a significant fraction of light speed, a grain of dust could carry enough energy to damage or destroy parts of a spacecraft upon impact. So shielding becomes a critical issue, not just protection from radiation, but from physical collisions at extreme speeds. Now there's another factor, acceleration itself. To reach these speeds, you would need to accelerate continuously over a long period, and that acceleration must be controlled. Too rapid, and it becomes unsafe for anything inside. Too slow, and the journey becomes impractically long. So there's a balance to find. A way to apply force steadily, gently enough for a human or delicate equipment, but long enough to build up significant speed. Now, from a human perspective, even reaching a small fraction of light speed would be transformative. At 10% of light speed, the nearest star system, Proxima Centauri, could be reached in about 40 years. Still a long journey, but within the span of a human lifetime. At 20%, that time is cut roughly in half. At higher speeds, time dilation begins to play a more noticeable role. The travellers would experience slightly less time than those who remain on Earth. Not dramatically at first, but increasingly so as speed increases. Now, reaching speeds where time dilation becomes truly significant, where years for you correspond to decades or centuries for others, would require velocities extremely close to light speed. And that brings us back to the energy problem. Each step closer becomes harder, more demanding, more resource-intensive. So while it is possible in principle to approach the speed of light, in practice, the challenges grow quickly. Now, there's something quietly important about this. The limit is not just theoretical. It shapes what is achievable. It defines the boundaries of exploration. But it doesn't make exploration impossible. It simply changes its scale. Now, imagine a future where technology has advanced far beyond what we have today. More efficient energy sources, more advanced materials, better ways to protect and guide spacecraft. In such a future, reaching a significant fraction of light speed might become feasible. Not easy, not routine, but possible. And even at those speeds, the effects we've been discussing would begin to matter. Time would pass differently. Distances would contract. The appearance of the universe would change. Now, there's another interesting possibility. Instead of trying to push a spacecraft faster and faster, we might find ways to take advantage of the structure of spacetime itself. Ideas like warp drives or wormholes are often discussed in this context. Concepts where the spacecraft doesn't move through space in the usual way, but where space itself is manipulated. These ideas are still highly speculative. They rely on forms of matter or energy that we don't yet know how to create or control. But they highlight something important. There may be more than one way to think about reaching distant places, not just by increasing speed, but by changing the path. Now, for the moment, those ideas remain theoretical. But the question itself, could we ever get close, has a grounded answer. Yes, in principle. We already have with particles. We may one day with small probes, and perhaps much further in the future with larger systems. but reaching the exact speed of light will remain out of reach for anything with mass. That boundary holds. Now, there's something quietly inspiring about that. The idea that even with limits, there is still so much space to explore, so much room to approach, to understand, to experience. We don't need to reach the absolute limit to see its effects, to feel its implications, to watch the universe change in response to our motion. Before anything else becomes a problem, before the engines reach their limits or the energy requirements begin to feel impossible, there's something much closer to you that quietly defines what this journey could actually be like. Your body, your mind, the way you perceive and process the world around you. Because even if we imagine that all the engineering challenges have been solved, that a spacecraft can accelerate smoothly to an extraordinary fraction of the speed of light, the question doesn't end there. It shifts inward. What would it feel like to be inside that environment, not just physically, but mentally? And how far could a human being actually go before those limits begin to matter? Now, at first, it might seem like speed itself would be the main issue. But as we've already touched on, once acceleration stabilizes, motion doesn't feel like motion. If your spacecraft accelerates gradually, gently, you might feel a steady force, something similar to gravity, pressing you into your seat or toward the floor. But once that acceleration becomes constant or stops, that sensation fades. At that point, you're simply moving, and motion by itself doesn't create discomfort. So in terms of raw speed, your body doesn't directly register how fast you're going. You don't feel 10% of light speed. You don't feel 90%. You feel acceleration. And if that acceleration is managed carefully, your body could in principle tolerate the journey. Now there's something interesting about that. It means that from a purely physical sensation standpoint, travelling at extreme speeds could feel surprisingly calm, steady, even peaceful. But that doesn't mean there are no limits, because the challenges begin to appear in more subtle ways. Now consider the environment inside the spacecraft. If the ship is designed to accelerate continuously, it could create an artificial gravity, a gentle, constant force pulling you in one direction. This could make it easier to move, to stand, to function in a way that feels familiar. But that same acceleration, if too strong, becomes a problem. The human body can only tolerate so much sustained force. At higher accelerations, blood begins to shift. Circulation becomes more difficult. Vision can narrow. Eventually, consciousness can be affected. So any realistic journey would need to balance acceleration carefully. Strong enough to build up speed, gentle enough to remain safe. Now, assuming that balance is achieved, and the spacecraft reaches a high, steady velocity, the physical strain of motion itself becomes minimal. But the environment of space introduces other challenges. Radiation, for example. At everyday speed, space radiation is already a concern. Cosmic rays, high-energy particles travelling through space, can interact with your body and with the materials of the spacecraft. But at high speeds, especially as you approach a significant fraction of the speed of light, this problem becomes more serious. Earlier, we talked about how light ahead of you becomes blue-shifted, increasing in energy. The same applies to other forms of radiation. Particles that might normally be relatively harmless can become far more energetic when you encounter them at high speed. From your perspective, they are rushing toward you. Their energy increases, and that means they can penetrate more deeply, cause more damage, and require more robust shielding. So the spacecraft would need to protect you, not just from the usual hazards of space, but from an intensified environment created by your own motion. Now, consider something even smaller. Dust. Tiny particles drifting through space. At low speeds, they're not much of a concern. But at a significant fraction of the light speed, even a microscopic grain can carry a large amount of kinetic energy. A collision with such a particle could damage the spacecraft, or, if unshielded, pose a risk to anything inside. So again, protection becomes critical, not just from radiation, but from physical impact at extreme speeds. Now, these are engineering challenges, but they connect directly to human safety, to your ability to remain protected, stable, and comfortable throughout the journey. But beyond the physical, there's another layer: your mind. Because even if your body is safe, even if the environment is controlled, the experience itself would be unlike anything we've known. Now, at first, it might feel normal. The interior of the spacecraft remains consistent. Your routines develop. You eat, sleep, think, perhaps work or observe. Time, from your perspective, flows as it always has. But there's a subtle shift in awareness that could begin to take shape. The knowledge that outside, time is passing differently. That while your days unfold normally, the world you left behind is moving forward at a different pace. Now, this isn't something you would feel moment to moment. It's not a sensation. It's a realization, one that could grow over time. Now, imagine being on such a journey for months or years. You remain connected, perhaps, through communication, messages sent and received. But as your speed increases, those communications become more complex. Signals take time. The differences in time between you and Earth grow, and eventually that connection begins to feel more distant. Not just in space, but in time. Now, from a psychological perspective, that could be significant. Humans are deeply connected to shared time, to the idea that we are moving forward together with others. But here, that shared timeline begins to diverge. You're still part of the same universe, but your experience of time is no longer aligned with those you left behind. Now, some people might find that fascinating, a kind of quiet detachment, a sense of stepping outside the usual flow of time, but others might find it more difficult, a sense of separation, of being out of sync. Now, there's also the matter of perception. Earlier we talked about how the universe begins to look different at high speeds. Stars clustering ahead, light shifting in colour, brightness changing. From a sensory perspective, this would require adaptation. Your brain would need to interpret a view that doesn't match your previous experience. At first, this might feel unusual, but over time, your perception would likely adjust. Humans are remarkably adaptable when it comes to sensory input. We learn to interpret new environments, to find patterns, to make sense of unfamiliar views. So while the universe might look different, it wouldn't necessarily feel disorienting once you've adapted. Now, there's another aspect of perception that becomes important: time itself, not in terms of physics, but in terms of how it feels. Even though your clock ticks normally, your awareness of time could shift based on context. Long journeys in confined spaces can alter the way we experience time. Days can feel longer or shorter, depending on routine, environment, and mental state. So maintaining a stable, healthy, psychological environment would be essential. Structure, variation, connection. All of these would play a role in keeping the experience grounded. Now, there's one more subtle point: identity. Our sense of who we are is tied in part to continuity, to the idea that we are moving forward through time alongside others. But in this scenario, that continuity becomes more personal, more isolated. You are still moving forward, but not in the same way as those outside your spacecraft. Now, this doesn't break identity, but it changes the context in which it exists. You become, in a sense, part of a different timeline, not separate from the universe, but moving through it differently. Now, there's something quietly profound about that. The idea that motion can change not just your physical experience, but your relationship to time itself. Now, stepping back slightly, it's clear that the human limits are not defined by a single factor, not just acceleration, not just radiation, not just perception, but a combination of all of these: physical safety, environmental control, psychological stability, all working together. Now, could we overcome these challenges? In principle, many of them could be managed with advanced technology, careful design, thoughtful planning. but they remain part of the equation, part of what defines how far we can go. That even at the most extreme edges of physics, the human experience remains central. What we feel, what we perceive, how we understand our place in the universe. What does it tell us about our relationship with time, space, and the universe itself? Somewhere along the way, the focus quietly shifts, not away from the science, but beyond it. Because after moving through all of this, the changing clocks, the shrinking distances, the shifting light, the growing energy, something else begins to settle in. Not a new equation, not another effect, but a different kind of understanding. A quieter one. Light speed stops feeling like just a number. It becomes something more like a boundary that shapes how the universe works at its deepest level. Now, it's easy to think of it as simply the fastest possible speed. Nothing can go faster, and that's the end of it. But what we've seen is that it's not just about speed, it's about how space and time are connected, how motion changes experience, how reality itself adjusts depending on how you move through it. And that's where the meaning begins to emerge, not in the idea of reaching light speed, but in what happens as you approach it. Because everything we've explored lives in that approach. Time slowing, distances shrinking, the universe changing its appearance, all of it unfolding gradually, gently, as you move closer to that limit. And that suggests something important. You don't need to reach the boundary to feel its effects. The boundary itself is defined by what happens near it. Now, there's something quietly elegant about that. The universe doesn't hide its structure completely. It reveals it in layers. As you move further from everyday experience, those deeper layers begin to show. And relativity is one of those layers, a way of describing reality that only becomes visible when you step outside the familiar range. Now think about how different this is from the way we usually imagine the world. We tend to think of space as fixed, time as steady, events as unfolding in a shared sequence. But here, those ideas soften. Not because they're wrong, but because they're incomplete. They're approximations, useful ones, but limited to a certain range of experience, and when you move beyond that range, the universe asks you to expand your understanding, to accept that time is not universal, that distance is not fixed, that observation depends on motion. Now there's something surprisingly calm about that realization. It doesn't make the universe chaotic, it makes it more consistent, more structured. Because instead of forcing everything into a single, absolute framework, it allows multiple perspectives to coexist, each one valid, each one connected. Now, return for a moment to the idea of travelling at high speed. Inside the spacecraft, everything feels normal. Your thoughts, your body, your perception of time, all steady, all familiar. And yet outside, things are different. Time moves at a different rate. Distances behave differently. The universe itself appears changed. And that contrast tells us something. Reality is not just what is out there, it's also how you move through it. Now there's a deeper layer to that idea, because it means that experience is not separate from the structure of the universe, it's part of it. Your motion, your path, your frame of reference all shape what you observe, and that doesn't make your experience less real, it makes it more specific, more personal. Now there's another quiet implication. The speed of light is not just a limit on motion, it's a limit on how quickly information can travel, on how quickly cause can lead to effect, and that gives it a kind of role in maintaining order. It ensures that events remain connected in a consistent way, that cause precedes effect, that the universe doesn't unravel into contradictions. So in that sense, light speed is not just a boundary, it's a safeguard. Now there's something reassuring in that. Even as our intuition breaks down, even as time and space behave in unfamiliar ways, the deeper structure holds. The universe remains coherent. Now think again about light itself. Photons travelling across vast distances, carrying information from distant stars to your eyes. From your perspective, That journey takes time. From their path, it does not. And yet, the connection is real. You see the star, you receive its light, the information arrives, and that duality, time passing for you, no time passing along the path, reflects the larger theme we've been exploring. Different perspectives, same reality. Now, as everything begins to settle, there's a kind of stillness in the idea. You don't need to imagine reaching the speed of light. You don't need to push all the way to that boundary, because even here where you are, the same structure exists. Time flows for you. Space extends around you. Light connects you to distant places, and all of it follows the same rules, just expressed in a way that feels familiar at your scale. Now there's one final thought to rest with. The universe is not built around our intuition. Our intuition is built from a small part of the universe, and when we step beyond that part, when we explore ideas like light speed, we're not breaking reality, we're expanding our understanding of it. And in doing so, we begin to see something deeper. That reality is flexible in ways we don't usually notice. That space and time are not separate but intertwined. That motion shapes experience, and that even at the most extreme limits, everything remains connected. Now, as this journey comes to a quiet pause, there's no need to resolve everything. No need to hold all the details at once. It's enough to carry the feeling of it. A universe where speed shapes time, where distance depends on motion, where light defines the structure of what is possible, and where, even at the edge of understanding, there is still a kind of calm consistency holding everything together. And with that, the question of travelling at light speed becomes something slightly different. Not just a thought experiment, but a window, a way of seeing how the universe works when you look just a little deeper than usual. And as that idea settles, gently, it leaves you with a sense that even the most extreme limits are not barriers to understanding. They're invitations to look closer, to think differently, and to notice how much of reality is quietly waiting just beyond what feels obvious.